Welcome, everyone. This is Michael Gibbs from Go Cloud Architects. I'm so excited to be here with you today. Today, to let you know what we're going to be doing is we're going to be doing and teaching an AWS Advanced Networking Bootcamp. And it's going to be a wonderful, wonderful, wonderful time. Now, let me tell you a little bit about the bootcamp and what we do and why we do it and the way we do it so I can give you some insight as to what we're going to be doing for the next week. For those of you that don't know me, my name is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects. And we're an organization that's really dedicated towards building cloud computing and networking careers. As everybody really knows, the cloud is nothing more than a virtualized network in a data center, and I love the network. In fact, I've been working on the network for so long, it's all I really remember. Back in the first cloud I worked on was the Frame Relay Cloud back in 1997. Then I worked on the ATM cloud, the VPLS cloud, the BGP VPN. So I've been working with clouds now for 25 years, and I've loved every last minute of it. So I'm one of the original Cisco certified internet experts. I spent a decade working for Cisco, and I've been involved in the design for most of the world's largest internet service providers. And I am just so excited to be here with you today. I'm going to let you know the format for the class because it's going to be a little different. I want to make this as close as possible to a real live training classroom experience for you. So what we're going to do is follows. We're basically going to teach for approximately 20 minutes, and then we're going to give you guys about 10 minutes to actually ask questions. And by doing it this way, 10 minutes of presentation, and it sounds like there's some background noise, Chris, in the background. So 20 minutes of presentation and 10 minutes of actual question and answer. I want you all to become great. Now, as many of you know, at Go Cloud Architects, we typically focus just on architecture. And as architects, we're system designers. But you know what? I've been having a lot of fun. We've been creating a lot of engineering courses as well. I've been working with some of the Linux engineers that are here. I've been working with some of the cloud engineers that are making some of our cloud engineering training. And you know what? I'm bringing in an awesome engineer, and we're going to do a bonus round tonight and a few other days per week. I'm super excited to say that my good buddy Imran Takur is going to come in, and not only are we going to do the architecture training from 12 to 3, but some days in the evenings, including tonight, we're actually going to do some hands-on configuration. We'll build some VPCs. We'll do some VPC peering. We'll do all kinds of load balancer work and maybe some load balancer sandwiches, and we're going to get really, really, really heavy. So we're going to give you both the cloud infrastructure architect perspective, which is my world. I'm a CCIE. My CCIE number is 7417. And my good buddy Imran Takur, who has dual CCIEs, he's got 25 years of networking experience. He's an aviatric multi-cloud network professional engineer, is going to come in and do some hands-on stuff with you guys later today. It'll be after this class. So we're going to have some bonus classes going on all week to make it an incredibly good experience for you. Now, when we run this class, a little bit of housekeeping because our class is going to be run very differently. There's what you need to know for the exam, which is basically so easy. And then there's what you need to get hired, which is so much more. In the context of this week, we're going to balance it out. We only have 1 week to do this, so we don't have the ability to give you all that you need. But I want to make sure you understand what is the network. I want to make sure you understand how networking works. And I'm going to make sure you get some of the other really critical things you need. We're going to go into BGP, for example, because you need to know BGP, and it's not covered in this course. So we need to do that, and we're going to give that to you. We're going to explain what routers are and what switches are and what they do, because you're going to need that. So the way we're going to do this is we're going to start today, and bear with us. We're going to spend about 60 minutes or so, maybe 90 minutes on the foundations of networking. Because if I just teach the advanced networking concepts without teaching the foundations, I'm worried that a lot of you are going to miss a lot of critical things. As someone that's been in the network for decades, here's what I can tell you. If the network doesn't work, nothing works. If the network is optimal, everything is optimal. And you know, after 25 years of networking, being one of the original CCIEs back when it was a 2-day test, consulting to everyone, I got to tell you, nearly almost all the problems you'll deal with in your life are related to the network not being as great as it needs to be. So we're going to spend a lot of time on the network, and I just wanted to let you know why. So when we talk today, it's going to start off, we're going to talk about what is networking. We're going to talk about some routers. We're going to talk about some switches. We're going to talk about some VLANs. Then we will get into the AWS. And then when we start approaching things like direct connections where BGP is required, well, then we're going to cover that as well, because I want to give you more, because I want you guys to be ready to go. I want you guys all getting cloud hired. So if you're excited, if you're ready to start training, if you want to learn career skills and certification skills, put hashtag cloud hired and let's get to work, everyone. So let's begin. What is networking? I want to start there, and I know it sounds very fundamental, but I want to start there. What is networking? Networking is connecting of computer systems. That's what networking is, and it's really important. It's the connection of the computer systems. This is the most critical tenet of networking. It is the connection of your computer systems. The network is the plumbing that enables everything to talk to each other. So no network, no website. No network, you can't attach to your servers. Nothing. So the network is the plumbing that connects your computers. So now what is that network? Well, it's routers. We'll talk about what routers are. It's switches. We'll talk about what switches do to some degree. It's cables, copper cables, fiber optic cables, LAN and WAN connections. That's networking. Networking is not load balancers. Networking is routers, switches, wide area connections, local area connections, and that's it. That is the network. So let's talk about what those networking things are. So let's walk through an actual network. And we're going to spend a few minutes talking about these networking fundamentals before we get here, because I want you to understand how it works. It's just so essential. So let's pretend for an example. Let me give you a visual representation of a network full of routers and switches over here. So let's look at what happens. In this environment, which you'll be able to see in about, we're going to actually talking about, this is networking in action. So let's say you've got a user on PC1, and let's say the user wants to reach something that's on PC2. So for example, if I'm at PC1, and when I get to PC1, there's a web server at 172.16.5.9. You can see it, it's at PC2 on the bottom of my screen here. You can see it, it's over here on the bottom. If I am a user over here, and I want to connect to this site down here, I've got to get my traffic there. So this is what occurs from routing. I want routing to make sense to everyone. So what happens, I'm a user, I'm on my PC1, and I want to hit the website that's PC2. So I enter, well, I have the IP address. So I enter in my web browser 172.16.5.9. My web browser pulls it up, and now my host wants to connect to this server. So the first thing that happens is my PC looks and says, do I have a route to 172.16.5.9? And guess what? The PC is not a router. It doesn't have a route in its routing table, and it has absolutely no idea how to reach 172.16.5.9. But what does this one PC have? This PC has a route that says, if you don't know where to go, send your traffic to router 1. So what happens is the PC, and if you're on your computer, and if you're on a Unix system and you do ifconfig, and if you're on a Windows system and you go from the command prompt and you type ipconfig/all, what you'll see is something called the default gateway, which is the PC's router. If you don't know where to go, send your traffic to the router. So what's going to happen is when PC1 wants to talk to PC2, it looks in its routing table, and it has a default route that says, send your traffic to router 1. Now, router 1 has this traffic, and router 1 says, do I have a path to 172.16.5.0./24 subnet? And router 1 says, guess what? I know how to get there. What I have to do is I have to hot potato, and I have to send my traffic to router 2. So I send the traffic to router 2. Router 2 now does a lookup in its routing table, and it says, do I know how to reach 172.16.5.0? And router 2 says, I sure do. Take that gigabit Ethernet link and go to router 3. Router 3 gets to the routing table, and the packet gets there, and the router says, do I know how to reach 172.16.5.0? And the router says, yes, I do. It is directly connected. I have a directly connected route. So the router does an ARP broadcast, which says, who has the MAC address for 172.16.5.9? 172.16.5.9 says, I have that MAC address. 172.16.5.9, which is PC2, then says, how do I reach PC1 of 172.168.1.2? So PC2 says, I know how to get there. I'm going to take my default gateway to router 3. When that packet gets to router 3, it says, wait, I know how to get to PC1. I'm going to go to router 2. And router 2 looks in its routing table and says, wait, I know how to get to router PC1. I'm going to go to router 1. And when it hits router 1, router 1 is going to say, I know how to reach this. I know how to reach this because it's directly connected. It's going to send an ARP broadcast. It's going to say, who has the MAC address to 172.168.1.2? PC1 is going to respond. And these two guys are talking to each other. And that's how networking occurs. Networking provides the path, and networking provides the intelligence to get your traffic from point A to point B. If you just had a wire between two locations, but you didn't have the route or the path to get there, you still couldn't get there. So I want you to really think about networking, and we'll talk about routing a lot, but I just want you to think of it this way. Let's say you wanted to go to a friend's house that is 1,000 miles away. If you have a car, but you don't know how to reach your friend's house, it doesn't matter how many highways there are, you still can't get there. So what do routers do? What does the network do? The network builds a map of all the roads, just like your GPS does. So you can say, I want to go to my friend Chris's house or my friend Alonzo's house. You get in your car and it says, make a left here, make a right. That's what the network does. The network determines how to get your traffic through the network. Oh, wow, Eric, I'm so happy to see you there. So, these are kind of those kind of things that we're talking about. This is what networking is. So I want you to get there. Now, when we talk about networking, I want to talk about the basics really, really fast. And when I talk about the basics, I want to talk about the OSI model. So when you're a networking person, you spend a lot of time with this OSI model. And people that know me, they're like, Mike, you hate theoretical frameworks. Mike, you hate stuff that it's not concrete. But the answer is, I love this model. And here's the reason I do. In networking, everything we network people do is between layer 1 and layer 3 for the networking professionals of the world. So let's talk about what these are. Why does this OSI model matter so much? Well, it matters because when things break, and I promise you, if you work in tech, things will break. They're going to break a lot. You've got to have a troubleshooting methodology. And not only do you have to have a troubleshooting methodology, you have to have a systematic approach to communication. When a doctor calls another doctor and says the patient has a maculopapular rash, the doctor on the other end of the phone call knows what that means. As a network architect, if I tell somebody we've got a physical problem, a physical cabling problem, the other person knows what that means. So in order to troubleshoot, in order to debug, in order to do things, we've got to have a common language. So the common language is the OSI, or the Open Systems Interconnect model. And what happened is this 7-layer model that kind of explains to us what happened so we know how to work. At networking, it's really layers 1 through 3. Occasionally we get involved into layer 4, but I want to cover them all because you're going to have to troubleshoot all layers of the stack. We're going to begin at the bottom, or the wire, the physical layer. The physical layer is the cabling between your routers. So you have two devices and they don't have any kind of connection between them. They can't talk to each other. So if you built a house on an island in the ocean and there was no road to it, you couldn't reach it without a boat. So the physical layer is going to be layer 1, and that's going to be either a copper wire or a fiber optic connection. So when you get your direct connection to AWS, for example, and you stick the lasers inside of your switch that plug into your WAN provider, that's your physical layer. The single mode fiber optic cable, that's layer 1. That is the single layer, the physical layer. Now, when we're dealing with networking, we also have a layer 2, which is the data link layer. So with the physical layer, we're basically transferring photons if we're dealing with lasers, or electrons if it's a wire. The data link layer, or layer 2, is where our network card is. So the Ethernet card in your computer, layer 2. The wireless access point, layer 2. The frame relay that we used to use Layer 2, a MAC address, layer 2. So layer 2 is a hard-coded address for communication. So layer 1 wire, layer 2 card or data link layer. Now layer 3, this is where the magic happens with networking. This is where your IP addressing is. This is where your routing is, your path determination is. And what we're actually transmitting at layer 3 is something called a packet. So layer 3 is basically figure out, your IP addressing. Layer 4 of this model, and I don't want to stay on it forever, layer 4 is related to the transport layer. So realistically speaking here, we can send our data via TCP, UDP, or ICMP. We'll briefly talk about it now, but we'll talk about it more in a minute. You use the protocol, transmission control protocol, when you need reliable transport, and we'll talk about that. So if I needed to send a file to one of you and guarantee that you receive the file, I would use the transfer control protocol. But if I'm streaming video to you right now, I'm going to use the UDP because I want real-time data. So the way you send your data in networking, and we'll get to that at some point through this course, is based upon the kind of data that you're sending. Now, layer 5, which is not a networking thing, the session layer is really about, controlling the session between hosts. Layer 6, or the presentation layer, again, not a networking thing, but this is where encryption does occur. Layer 7 is what you as the user use. That's the application layer. So think application layer, layer 7. So one more time. Physical wire, layer 1, we transfer bits, electrons, or photons. Layer 2, the data link layer. This is the Ethernet card with a MAC address. It's a physical address, and we're dealing with frames. Layer 3, we're dealing with the network layer. We're dealing with the IP addressing things, and we're realistically sending packets. Layer 4, the transport layer, we're dealing with TCP for reliable, UDP for real time, and we're dealing with ICMP for network control, and these are called segments. And then at layer 5, we're actually dealing with basically managing the session for interhost communication. We're dealing with sockets. Layer 6 is the presentation layer, think encryption, and layer 7 is what the users use. So I know we did a little bit of academic work there, but I just wanted to make sure of it. So let's get our fundamentals down real quick. Let's talk about the difference between a LAN and a WAN, because we're going to need this when we get to the cloud. A LAN is a local area network. So think inside of a building, local area network. Inside of a campus, local area network. An availability zone, local area network. What's the key of a local area network? It's local. It's not a big separation of things. So local area network is local. Wide area network, by comparison, is not. I get a connection to my friend Ian's house in London. That is a wide area network connection. I get a connection between my location and the AWS availability zone in Ohio. That is a wide area connection, because Palm Beach to Ohio is like 1,500 miles, 1,300 miles, whatever it is. It's a long distance. Local area connection, fast, low latency, high performance. If I want a 100 gig connection between two things, I buy a 100 gig card on both sides. I run my own cable, and I don't pay for the connection. Wide area connection, New York to London. I got to call AT&T, Verizon, Vodafone, or somebody, or BT, and I've got to order a connection. It's going to take weeks, and they're going to build me a connection, and it's going to be slow, and it's going to be real expensive. So that is what we're talking about. So let's look at, make it real quick so you guys get a better feel for a LAN. A LAN is going to be very simple. You've got two buildings, for example, and these two buildings, what you can actually see is we've got two sets of switches. And we've got two sets of switches. They're connected, but everybody's close to each other. Real high performance, real high speed networking, and everybody's having all kinds of fun. We absolutely love this. So that's what's going on. So now, when we're talking about LANs, and I know we're kind of hitting you with a lot of network stuff right now before we get into the AWS stuff. And I'm doing this for a reason. I want you guys to have the fundamentals. So when we talk about an 802.1q tag with the direct connections, you're going to understand. Because I don't want you memorizing stuff. I want you knowing it. I want you, when you guys go on your interviews, for people to know you so well, they're like, I need that person on my team. And that comes from depth of knowledge. So let's go build some good knowledge. So let's look at the concept of a virtual LAN. So networking, as I mentioned, is routers and switches. Routers direct your traffic through the network. Switches is where your users are plugged into. If you guys aren't familiar with the switch, I happen to have a couple of them right next to me. Here you can see in this picture, you can see my actual switch. I'm going to keep it here till I can actually see it so I can explain the concept of a virtual LAN. Note, when you guys all see the switch, which is sitting on top of my head right now, you'll notice there's a whole bunch of Ethernet ports where you plug your servers in. This is a typical switch. Now, right now, out of the box, everybody in this single switch can talk to each other, which might be great. But what if I didn't want that to occur? What if, for example, I had some finance users over here, some accounting users over here, and some QA users over there, and I didn't want them to talk to each other? Could I do that? Could I keep them separate on the same switch? Could I find a way to increase my security? And the answer is I can, and that's called a virtual LAN. So go back to that switch that looked like a pizza box with a whole bunch of Ethernet ports. Let's say I grouped 10 ports together and called it accounting, and another 10 ports together and called it finance, and another 10 and called it dev, and another 10 that called it test. Dev could talk to dev, test could talk to test, accounting could talk to accounting, and finance could talk to finance, but nobody else would talk to each other. It's called a VLAN. So that works. Just basically virtualization of a switch. Server virtualization, VLAN virtualization, which came thing first. VLAN's 30-some years old, virtualizing a switch. VMware ESXi about 10, 15 years later. Now you know where it all comes from. So now let's look at it. So I want to walk you through some architectural situations of switching real quick. So let's go back to my diagram, and well, I'm not sure. Well, I'll do what I can to try and make this diagram look a little better, if at all possible, given me being in the corner. But let's try to move this up. Sometimes slides don't necessarily fit YouTube as pretty as you'd like them. But okay, so let's do this. So now let's say I've got two switches. Just like the previous switch that I had on top of my head, I chopped up into 4 VLANs. This is really important because we're going to be dealing with this when we deal with the 802.1q tagging for the direct connection. So that's why I'm spending some time here. I took my switch and I created 4 VLANs in that switch. VLAN A, let's call that accounting. VLAN B, let's call it finance. VLAN C, let's call it dev. And VLAN D, let's call it test. I've then decided to create 4 additional VLANs on another switch. And they're basically accounting, finance, dev, and test, the same ones. So now I want to get my switches communicating to each other. I want you to understand what my options are, because when you understand what these options are, it'll make lots and lots of sense to you. So what I could do is as follows. I could run a cable between VLAN A and VLAN A, and then VLAN A will be able to talk to each other on both sides. Then I could run a cable from VLAN B to VLAN B, and then VLAN B could talk to VLAN B over this cable. I could run a cable from VLAN C over to VLAN C, and then C could talk to C through this cable. And then I could run a cable from VLAN D to a cable from VLAN D. Everybody can talk to everybody, and I've got 4 cables, and everything is perfect. Now, this is perfect. Now, if you and you could conceivably do this, imagine doing this with AWS. Every single person runs a new cable to AWS. AWS has 1 million customers. 1 million cables would need to be run by AWS. Under the ground, under the ocean, you get the concept. So what is this? So now let's talk about trunking. So previously, I just told you that we could run a cable from VLAN A to VLAN B. And we could run a cable from VLAN B to VLAN B, and a cable from VLAN C to VLAN C, and a cable from VLAN D to VLAN D. And it's all going to work, and it's going to work awesome. But what if we only had one cable? What if we had one fiber optic connection between our switches? Just one cable. How could we do this? How could we get VLAN A talking to VLAN A and VLAN B? We've got a single cable. So, by the way, this is one of the first virtual private networks that was out there. What did we do? We came up with the concept of a trunk port. And basically what a trunk port is you run a single cable or a group of cables between 2 switches. Then what you do is you add a tag to the frame. So let's say you've got something from VLAN A that wants to reach VLAN A. When VLAN A goes on the wire, the switch on the way to the wire puts a tag that says VLAN A. And when data leaves B, it has a tag that says VLAN B. It's called an 802.1q tag. And then VLAN C will pop its tag that says it's on VLAN C. And then VLAN D will put its tag on it. Now, meanwhile, these frames start going over the trunk to the far end switch. Now, the far end switch says, wait a second, I've got a frame that's destined for VLAN A because it's got VLAN A's .1q tag. Strips the tag, drops the message into VLAN A. Then the next frame comes in and the switch says, wait, it's destined for VLAN B. Removes the tag and puts it here. It does the same thing for C and D. So what is an 802.1q tag? What is the thing that makes the direct connection possible? You basically take your Ethernet frame, you smack a tag on it. That tag that you smacked on it tells this wire to keep your traffic separated. So when you connect to AWS and you send them a VLAN, you know they've got a layer 2 network that they're sending these VLANs, that they're bridging your traffic back to your VPC across the AWS network. And this is how and why this works. So what we'll do is we're going to go for a few more minutes. I'm sure there's going to be some networking questions. We'll answer your networking questions. And then after we do this stuff, we're going to start getting into the AWS stuff, which is really fun and exciting. But I want you guys to all make sure we level set on the network thing. So we're going to talk about a couple more networking things, and then we are going to go back to the AWS content. But I wanted to give you something. So I want you to actually give you some look for some of the things and feelings, the things going on. We're going to walk through some logical views of some networks. So when you connect two locations, realistically speaking, what happens is, let's say I've got a site in New York and a site in San Francisco. What happens is you typically buy a link to your service provider, your AT&T and Verizon. And what will happen is they will send you over their private network to your ultimate destination. So that's what these things typically look like. There's going to be switches that the service providers use to go from either one telco to another telco or there. But I just wanted to make sure this is pretty much there. So let's look at the other type. So it used to be when we did WANs, we did something called serial points, T1, T3, frame relay, ATM, various cloud services. But now we're typically doing Ethernet. So how does this work? And by the way, this is going to look a lot like the way you'd set up a direct connection. So the way typically Ethernet WANs work, and this is going to be very alike to a direct connection, but we're going to spend a lot of time on direct connections, like possibly a half of a day because they're so important. So you've got the customer site, you connect it to a switch, the service provider switches your information over their network, and then it goes to your end. So guess what? Nothing's different whether it's a frame relay, ATM, or Ethernet. I just wanted to show the point that that's realistically what's going on. So let's look at one last thing. Let's look at look at the IP header, and then we're going to get into the AWS content. So we'll open up for some questions, and then we'll have fun with AWS content. So let's look at what's in a header of these frames. When a packet gets to a router, and it's a packet at layer 3, it's got a destination IP address. That's what the routers use. The routers look at the destination IP address and say, go out this interface, it's the closest one, or go out this interface, or go out this interface, or go out this interface. So there's a destination address. There's also a source IP address. By the way, guys and girls, everyone out there, where do you think this information that's part of a firewall or an access control list is able to get this information? The header of the packet. So the destination address, the source address. Okay, let's walk through. What is this header checksum? If the header checksum is basically a hash, that basically you run a one-way mathematical hash to show that the frame wasn't damaged. So basically, source address, destination address. The checksum just means your data is good. The protocol, this is where your TCP is or your UDP is. So source, destination address, protocol. Wait, that's what goes into an access control list. That's what goes into a security group. That's what goes into a firewall rule. Then what else do you have in this? You've got a length. That tells you how many bytes the packet is. You've got this thing called the DS field, degree of service. You can set that to red or high priority. And if you've made your network aware to look at the prioritization and send higher priority data over lower priority data, you can match that by taking your messages and changing them in the DS field. And then, of course, the version is which version of IP that we're using. So I hope we've had a little bit of fun doing some intro to networking concepts that we'll talk about before we actually go on and we'll do some AWS content. So I'd like to take a break for a few minutes. I'd like to answer some questions. I'm sure you guys have some. I want to make this the best experience. I want you guys to be able to ask questions. If there's something you want more of, I want you to tell us. If you guys need help with something, I want you to tell us. I just want to know that you guys have the absolute best experience and learn so much that we get you all cloud hired. So Chris, if you want to bring in some of the questions that have transpired, as we're waiting for questions to transpire, if you can hit the like button or tell others to join us. We love educating and training others. And if you can bring others or invite others, we'd be more than grateful. So Chris, if you want to bring in some of the questions that popped up. AfriP, how big of a perimeter would be considered a LAN? I don't really think there is a perimeter AfriP. It's really based on how big. So, you could create a LAN that would have data center, data center, data center, data center, data center, data center, and that whole data center building could be 5 miles, and it would still be a LAN because you're going to be using single mode fiber to connect them all. So that could still be considered a LAN. I don't really think there is necessarily a definition of 100 meters, but it's really how close and densely packed you can get it. Chris, you want to bring in the next one? Racine, are the frames carrying the source as well as the destination tags on the cable? Okay, Asim, the only tag they're actually carrying is an 802.1q tag or a Vlan tag. So the frames themselves always have a source MAC address and a destination MAC address, and that will definitely be there. But it's going to add that 802.1q tag. So it's going to basically take the frame. It's called encapsulation. It adds something. So yes, they will have a source MAC address and the destination MAC address, but they also, realistically speaking, are going to have that 802.1q tag. That's what the magic is. It's that 802.1q tag. Chris, you want to bring in the next one? Tailor-made media. What if A wants to connect to B, C, or D? Tailor-made media, they cannot without going through a router. So in the old days, we used to do this thing called a router on a stick, where basically we would create a trunk port between the switch to the router, and the router would route between VLANs. We haven't done that in about 20 years ago for anything other than a certification exam, but we used to do that about 20 years ago. What we do now is the switches themselves actually have router modules that sit inside the switches. And what we would do is we'd create a VLAN, and then we create an IP address for an IP interface for the VLAN. And then we would turn on our routing protocol, OSPF, EIGRP, intermediate systems to intermediate systems, and then route between VLANs. So that's what would occur. They can't tailor-made media. That's the whole point of VLANs, is they keep people from talking to each other. And then they use routers to connect the VLAN. So that's what you have to do. You actually have to set up your routing in order to make that happen, tailor-made media. And that's an excellent question, by the way. Achori Patrick, can I show you a picture of a socket tag? I don't know what you mean by a socket tag. A tag that we're talking about is at layer 2 of VLAN, so an 802.1q tag. And a socket is actually at layer 5, which is a TCP address, which is an IP address and a port number, so they're not really related. Dimple Patel, is WAN connection over a different country? Connecting country to country would be a WAN connection, but connecting a state to state would be a WAN connection. Even going from, say, Mysore to Bangalore, figure like 80 to 100 kilometers, that would be a WAN connection. So it could be, Patel, it could be going from India to Pakistan, that would be a WAN connection. It could be going from Delhi to Bangalore. It could be going from Mysore to Bangalore, even though that's not that far away. So a WAN connection, realistically speaking, is just over a wide area. So anytime you're dealing with, more than a couple of miles, and even a couple of miles could be considered a WAN connection. WAN just means longer distance. Would the connection between AWS services be a LAN is connected to the backbone? Predominantly, Abdul, predominantly most of those services are LAN services. Some of those other services are also WAN services, but in general, the most likely LAN, because you could call them LAN because even if you're using a serverless thing like DynamoDB, chances are it's going to be hosted in the same availability zone as you or one of the local availability zones. So that would still be considered a LAN. And that's one of the things that's so good about them, is you've got high performance. Are there switch-to-switch cable connections that do not run over trunk ports? Sure. You can do a switch-to-switch and just run a single cable, like a cable between VLAN 2 and VLAN 2 and VLAN 3 and VLAN 3. Lots of reasons that could be done. Generally speaking, people don't. They use trunk ports due to the flexibility. And they tell the trunk ports which VLANs they'd actually use. So you could set up multiple trunk ports. You could send VLANs 1 and 2 over a single trunk, and VLANs 3 and 4 over a single trunk, and VLANs 5 and 6. It doesn't matter, their traffic is separated, but you might actually want to do this for the following reason: to generate more bandwidth. So that is something you could do, but you typically wouldn't, for the complexity and for the simplicity of the trunk. Chris, are there more? Is a VLAN the same concept as a VPC? Not exactly. So a VLAN, realistically speaking, is a group of ports on a switch. A VPC, which some of the certification providers mistakenly call a virtual private network, is really a virtual private data center. So a virtual private network, for example, is basically you've got a public network like the internet, and you secure and encrypt your traffic privately over the public internet. But when you create that IPsec tunnel or a virtual private network, there's no servers there. There's no load balancers there. It's just connections. So when you're dealing with a VLAN, I'm going to go back to this tech with Mufaz, you're dealing with a grouping of a couple ports on a switch. Whereas a VPC is your virtual private data center. So your virtual private data center will have your IP addressing, they'll have your routing, they'll have your load balancers, they'll have your servers, they'll have your storage. So they're completely different tech with Mufaz. VLAN is a switch. Okay, so Perez the dev, what's the difference between a frame and a VLAN? Wow, that's a good one. So let's go back to that OSI mile, Perez the dev, because that is a really good question. Let's pull up this OSI model. Let me share the screen one more time, Perez the dev. So let's go back to this. At every layer of the OSI model, we transmit something different. So at the physical layer, let's say you got a wire like this. This wire just happens to be for my keyboard. For whatever reason, my keyboard's battery, I bought this super expensive Logitech thing, mount my keyboard, and the battery dies every 3 days. So I've got a physical wire over here to charge it in. What do we send on a wire? Electrons. So it's referred to as bits at layer 1, but really it's electrons. So at layer 2 of the data link layer, we send what's called a frame. And at layer 3 of the OSI layer, we send what's called a packet. So that's, realistically speaking, the name. So when you're in the VLAN, Perez the dev, you're communicating using layer 2 technologies, MAC addresses. So a frame is what's being used to communicate inside of the VLAN. So if server 1 says, here's a video of Mike's cat Cindy, and that's a file that's inside of the VLAN, all the other users inside of that VLAN will be able to see it. But when I send the message to you, Perez the dev, in the same VLAN, I'm going to send you a frame because we're both at layer 2. But if you and I were at layer 3, I would send you a packet. I hope that makes sense. If not, if you want to re-ask the question, I'll get back to it. Vijaya, in the case of an AWS site-to-site VPN, the on-premise subnet and the AWS subnet need to be different. Well, always your on-premise subnets will have to be different than the cloud provider subnets. In fact, anything outside of your VLAN will have to be on a different subnet. But the connection between the two has to be on the same subnet. So if you've got a 192.168.1.1/30, the opposite side of that WAN connection is going to be a 192.168.1.2/30. So both sides of any connection need to be on the same subnet. But if you've got a router that, let's say my hands are routers, the fingers that are pointing to each other, that's the direct connection. They need to be on the same subnet. But my thumbs are each going to be on a different subnet. So realistically speaking, you're always going to have a combination of subnets going on. So Abigail Marks, how fast are these packets being transferred? Are we talking the speed of light? Yeah, pretty much. So Abigail Marks, I want to let you know that even the speed of light, which is 186,000 miles per second, we're not getting that fast, but we're getting close. So I send a fiber optic connection to you, Abigail. I think you're in California. I could be wrong, but I'm going to pretend you're in California. I now have, let's assume we had a very long fiber optic connection between you and me for these 3,000 miles. It's going to take some time for me to send my data to you, even at the speed of light. So when I send a laser, the laser sends the light over the wire. Now the wire has what's called some resistance. The wire isn't straight air, so it's going to add some drag, so to speak, which is going to slow it down. But when we're dealing with cables and electrons, we're pretty close to the speed of light, Abigail. So it's moving very, very, very fast. Okay, Chris from my team has notified me that we've answered the max amount of questions that we can do to keep you guys up and moving on time. So we're going to get into some AWS stuff, which is going to be really fun. And then when we get to some routing inside of these things, we're going to do some really cool things. So before we begin, if you guys can let us know you're having a good time, hit the like button, tell others to join us, and type #CloudHired. The whole point of doing training is to get hired, not just to pass the certification. So we're going to go way above and beyond to give you a lot more than is necessary to pass the exam, because I want to get you all cloud hired. And tonight, and Chris from my team will tell us what time, but tonight my good buddy Imran with the dual CCIE, and I'm also a CCIE, we're going to come in and we're going to have some lab time, and it's going to be lots of fun. So let us know that you're here by #CloudHired and hit the like button, tell others to join us. We love when other people join us, and we're super excited to have you here. 5 p.m. Eastern, we are going to have Imran Takur, and we're going to come in and do a multi-hour hands-on lab. And I'm going to get my inner geek on with my buddy, and it's going to be really fun. I don't get to do it that often. So super excited about it. So let's talk about the AWS cloud and how it's organized. So when we talk about it, we're going to break this down into a couple of things. We're going to talk about regions, availability zones, local zones, and edge locations. So let's really bring it in. So I'm going to talk about the concept of a region. And what is a region? It is a huge geographic area. So the US is a region. Actually, it's 2 regions, but it could be a region. A region, think continent or some big area. Now, when we're dealing with these cloud providers, they have the concept of an availability zone. What's an availability zone? It's just a data center. That's it. So availability zone data center. So you're going to have these big geographic areas, and inside of these geographic regions, you're going to have data centers. And we're going to walk through each one, and we're going to get very detailed throughout this, but we got to start with the foundations. Get your foundation straight, ramp up fast. Don't get the foundation right. When we ramp up, we create problems. So the next thing we're going to talk about are local zones. So Abigail just asked, what is a wide area connection? And let's say, for example, I want to connect to the US East in Ohio and I'm in Florida. It's not fast. It's going to take time, 2-3 milliseconds to reach that data center. What if I need to access my servers faster? What if I need fast, speedy, high performance criticality? What if I need that so badly? I can't get it with the cloud because I've got to go 1,000 miles to get to the cloud provider. But what if on the way to the availability zone, I had a little mini data center where my direct connection might be, where I can access my servers quicker? That's what a local zone is. And we're going to talk a lot about that, local zones and edge computing, when we walk through it, but I want you to understand what it is. And then we will talk about edge locations, which are part of the content delivery network CloudFront. For those of you that are writing these nice messages, I am so grateful to have you here, and I'm thrilled to do this, and I really want to help you all. So thank you all for your nice messages. So let's walk through this. Let's look at it graphically. So when we look through this environment here, this is what it looks like. You can see this nice large geographic region, And you can see the data centers called the availability zones. You can see this is what it looks like. So that's the availability zone. Now let's talk about local zones. So previously I talked about the latency of reaching somebody far away. And what makes the data center in many cases so much better performance-wise than the cloud is when you're dealing with the cloud, you've got to get to the cloud. And if that cloud's 1,000 miles away, that can introduce some latency. Now, I want you to think about applications and latency. If I want to call my cat Cindy over a video conference call, and I'm in California for the week, and she's home in Palm Beach, and I have a video conference with my cat Cindy, if it takes me an extra 3 milliseconds to see my cat, it doesn't matter. It's meaningless. Now, let's pretend I'm a financial organization and I want to buy 800,000 shares of Cisco because there's good news. And then after I buy 800,000 shares of Cisco, I want to sell it because I made 3 cents per share. And now I want to buy 800,000 shares of Meta or Facebook. And then I want to trade that. And after that, I want to trade that. And I want to buy 800,000 shares of Amazon. And if I can buy it a nanosecond faster than my competition, I might be able to make 3 or 4 cents per share, but I'm doing that for 800,000 things. I may then sell that stock 3 seconds later and make another 3 cents on it per share. And I might do it again 1,000 times a day. And if I can do it better and faster and cheaper than my competition, that could be billions of dollars per year. So sometimes the latency that it takes to go from your data center to the cloud is so bad that it can kill an organization's competitive advantage. That's where the concept of the local zone comes from. The local zone effectively is as follows. It's a little mini data center that is closer to you than the actual availability zone. And you can put some of your stuff in there. So the way it's going to work is you'll opt in to create a local zone. You put your EC2 instances or your virtual machines, your load balancers, your containers in there. And now, let's say you connect to the direct connection location. Say this is right by the direct connection location. It's close to you. It's fast. The performance is good. It's pretty terrific. And that's still connected back. So you can use the cloud for where the cloud's good, and you can actually do this in a local zone. Now, there are a few local zones, such as the ones in LA, that give you the file system for Windows, Elastic MapReduce, Elastic Cache, RDS databases, and even dedicated hosts. So some of these local zones can get some pretty darn sophisticated and pretty capable. Why do the organizations do local zones? What's in it for them to create these local zones? Well, I'll tell you right now. If you need guaranteed performance and super performance better than you can get in the cloud, you've got 2 options. You stick it in your data center, or you stick it in a local zone. By providing the local zone, the cloud providers are trying to mitigate the need for you to do this in your own data center, making the cloud a more simple and elegant solution, giving you near data center-like performance in the cloud. Remember, the data center always performs better, but it's not agile, it's not as scalable. So that's all the good reasons why we're using the cloud. The cloud is amazing, but it has that latency problem. So as architects, we can't ignore the latency problem. We have to understand the workarounds to the latency problem. Let's talk a little bit more about local zones and look at what they look like visually. So typically speaking, this would be a good AWS representation of it. You got the concept of a local zones, you enable it, you'll extend your VPC to it, and then you'll run your applications. But let's look what it really looks like. You've got your region, and then you've got your data center, called an availability zone. And then you've got your local zone. So this is realistically what it's working for. Think about it this way. Think of it, let's try and make it look a little easier. So let's pretend over here, this is your data center. Let's whiteboard our way through this. And if you guys at any point want us to whiteboard anything this week to truly help you guys understand it, I'm happy to do some on-the-fly whiteboard sessions or really anything. Just let me know what you guys need. We're going to give you a great experience. So we have our data center. And let's say this is their direct connection facility. So look at it this way. We'd connect to the direct connection facility. And the direct connection facility, let's say, is kind of hosted right around the same place as your local zones. You got some servers in here, and then the rest of your stuff is here. So you can access your local performance when you need it. And at the same time, you've got your cloud performance. and your scalability factors for everything else. So that's realistically speaking what's going on here, right? Organizations are using local zones. So I wanted to make sure that was pretty clear to you guys. Now, the last part of the cloud's architectural layout are going to be the following. We're going to talk about something called edge locations. So love edge locations, love content delivery networks. We're going to spend a lot of time talking about content delivery networks, a lot of it. But right now, we're just going to have some fun. We're going to talk about some edge locations because edge locations and local zones are very different. Edge locations are for content delivery systems. The local zones that we just talked about are used for edge computing. So now let's talk about edge locations. An edge location is where the user is going to access the CloudFront content delivery network. And I'm going to walk you guys through a content delivery network just in case you're not sure. The edge locations provided by CloudFront provide a local access point for you to access the content delivery network. So edge locations are going to really help with performance, and they're really going to help with latency. And I'm going to walk you through how this works and why it works. So this is what these look like. So from an edge location perspective, you've got your geographic region, and you've got your data centers within these regions, and then you've got these edge locations. So now let's walk it through. So here's a user. They're sitting in their house. The user that's sitting in their house wants to connect to www.gocloudcareers.com. So the user enters www.gocloudcareers.com in their browser. The computer then does a DNS lookup and says, please give me the source IP address for www.gocloudcareers.com. An address is given to the user and sends the user's traffic to the edge location. So here we've got the user's traffic is sent to the edge location. Now, if the edge location has access to my traffic, the edge location will send the data right back to me, the user, and it'll go straight from the edge location to the user. That's optimal. Now, if I go to request www.gocloudcareers.com and I go to the edge location and the edge location doesn't have it, the edge location will stop at something that's called a regional cache. And then if it's not at the regional cache, it will go to the source website. If it's static content, it'll go to that S3 bucket. If it's dynamic content, it'll hit the load balancer in front of the EC2 instances, which will then stop at the regional cache, which will then stop at the edge location, which will then send the web page to me. Now, 10 minutes later, my wife decides to go to the www.gocloudcareers.com place. So now she sits here in the same place as me. She goes to the same edge location and is immediately, what's the word I'm looking for? So she immediately gets access to her information because she requested from the edge location, and then it immediately gets sent back to her. She requests it from the edge location, and it immediately gets sent back to her because I already requested it. So what do these edge locations do? They cache information. So what are the edge locations of the content delivery network CloudFront? They are where you, the user, enter the content delivery network. And it's where your information is cached to improve your speed, throughput, and performance. So let's talk about this. So I will go back to these. So let me just do one thing. I want to make sure because this kind of stuff over here has the potential to be a little bit tricky. So I want to make sure everybody understands these zone concepts. So I'll spend 2 minutes here. Are there any questions on the zones before we move on to the next content? Does anybody have any questions about the availability zones, the local zones, the edge locations, or is that clear to everyone? I want to make sure. Okay, Matthew Burke. Are edge locations the same as local zones? Absolutely not. So an edge location is where the user comes to access the content delivery network. You type www.cisco.com and you get a resolution to the Akamai content delivery network. You hit the Akamai content delivery network. That's the equivalent of an edge location. So we should all go visit Brandon Bowman's website. If he pops the link, He's got it hosted, and he's using CloudFront as a content delivery network. So everybody, let's show Brandon's website some love. Let's hit Brandon's website. Brandon is an exceptionally good cloud architect. So let's hit Brandon's website. That is where we hit the edge location through CloudFront. Now, by comparison, if I wanted to stick a server close to me, I can't stick my server in somebody else's content delivery network because that's something somebody else's. But I can put my server in another AWS-owned data center that they don't call an availability zone, that they call a local zone. So what is a local zone? It's an availability zone that's close to you. That's really all it is. It's an AWS data center that's not 1,000 miles away. They call it an edge location. So realistically speaking, that's it. A local zone is another AWS data center that's close to you. Whereas the CloudFront Content Delivery Network is a cache for web applications. The local zone are for your applications. Does that make sense, Matthew and others? If so, great. If not, just let me know in the chat box and I'll try it one more time. But availability zone, geographic region. Data center, availability zone. Data center close to you for speed and reduced latency. Local zone, content delivery network, edge locations. Asim has. How does one decide what to store in the local zone since it may have limited storage in a mini data center? Asim Hans, the only reason you ever would use a local zone is if you have low latency requirements. You would never use it otherwise. So if you've got extremely low latency requirements, you'll use a local zone. Otherwise, you can stick it all in your data center or stick it all in your cloud. There's no reason to do it. The whole point of the local zone is to not have to wait to go so far away. That's pretty much it. So an edge location is not like DNS. DNS maps a name to an IP address. DNS will, so if I type www.cisco.com, it gives me an IP address for the website. That is DNS. But a content delivery network speeds content to people. But here's the good news. We're going to spend about an hour covering content delivery networks. SM7. So when your info is in the cloud, is it in the both local zone or an AZ or both? SM7, for 95% of the populations, it'll never be in a local zone. For 95% of the population, it'll just be in their availability zones. For organizations that can't get away with the low performance of the cloud that need something faster, they will use local zones, but it's for a small number. Local zone is not something you put in the hosting data center. Local zone is another AWS data center that's closer to you. Now, Azure has the ability to run your workloads on the Azure software sitting in your data center, and that would be their version of a much improved version of a local zone. Which are higher in number, local zones or edge locations? There are going to be more edge locations that are out there, because is the edge location a physical zone like a local zone? Yep, an edge location is where it's a data center. It's got routers and switches and servers and caching, just like any other data center. Where is the regional cache located? There's various regional caches throughout the world. How do you get access to the local zone? Well, exactly what I had told you. The steps are as follows. You have to opt in to a local zone. Then you create a subnet in the local zone, and then you put your EC2 instance load balancers in that subnet. That's pretty much it. Okay, well, let's go back to coming into some content. I just want to try and do what we could to clean things up. So let's do this. Is everyone? Let's do some IP addressing stuff, and then we're going to get to the VPC. How much knowledge does everybody have about IP addressing? Are all you guys familiar with the private IP addresses and subnetting and things like that? If you've got great IP familiarity, type familiar in the chat box. And if you need a little bit, if you need more, let us know that you need some basic IP in the chat box, and then I'll give it to you. I want to know that we give you what you need, but don't bore you. Always confused. Cloud hired. Refresher would be nice. Let's do a refresher. Early bird gets the worm. They're the ones that are first to do it. So let's get there. Let's talk about IP addressing, because this is kind of important. everybody in the entire world, every device needs a unique address. We're going to be quick on this, but everybody needs a unique address. So I want to send data to Pierre in Canada. If let's say I want to send a mail to his physical address. If I don't have Pierre's address, I can't send it to him. If Pierre and his buddy have the same address, I can't send it to them because the mail won't know where to go. So every computer or every device that's out there needs to have an address, and it must be unique. If it's not unique, the mail will never get to you. Your data will not get to there. So we're going to have the concept of so let's talk about it. So every device has to have a unique address. Now, when we're dealing with IP addressing, we have a problem, a big problem. The problem that we have is going to be as follows. We don't have enough IP addresses. So like literally speaking, we don't have enough IP addresses. Because we don't have enough IP addresses, the Internet Engineering Task Force told us which IP addresses to use inside of our network. So inside of our systems, we're going to be using IP addressing from the private address space. The Internet Engineering Task Force told us to use these addresses. So we're going to be using the addresses that were given to us by the Internet Engineering Task Force, which means that nearly every organization in the entire world is going to be using the same IP addressing scheme. So we're going to have some challenges. If your business is using the 10.8 address space and another business is using a 10. Address space, and the business buys the other business, they can't talk to each other. When you're on the cloud and you want to peer VPC peering to somebody else that's using the same IP addresses, we have a problem. So we're going to talk about these addresses, and then later in the course, we're going to talk about how to fix these massive problems caused by the Internet Engineering Task Force, fix to the broken number of IP addresses. See, it's always a matter of something to fix something else. So understand that the private IP addresses that we're going to use are the 10.0.0/8 address space, the 172.16.0.0/12 address space, and the 192.168.0.0/16. All private addresses, for the most part, will be on there. I'm also going to talk for about 10 seconds, and then I don't ever want to talk about this again because it's history. I'm going to talk about IP address classes. When I was a kid and I started moving in networking, they had been phasing away IP address classes, and that was a long time ago. What happened is we used to have these Class A addresses that were a /8 with the subnet mask, and I don't know how. And there were a Class A with the subnet mask, and then we had a Class B, which were /16s, and then we had a Class C. And 1,000,001 years ago, everybody used these addresses. Now the problem and I'll have other things that I'll show it to you later. If we stuck this IP address on an Ethernet port, and we couldn't put more than 250 hosts in a subnet, just because we'd have 16 million addresses, we'd literally use them all up on a single subnet. So we had to break these giant things down, and that was something called subnetting. We can subnet down, we can supernet up. We call that classless interdomain routing. Basically, what CIDR means, because you'll see CIDR on your exams, is we no longer stick to the Class A, which you can see here, Class B, Class C, or Class D, which means we subnet or change the subnet mask by borrowing host bits and network bits. That's it. All we needed to say right then and there in 1:01. So just to let you know what that. So we don't use classful addresses. We haven't in about 2 decades, so I don't think we need to talk about too much. Now let's talk about subnetting for a second. We're going to briefly go over it. Now, if you guys are completely unfamiliar with subnetting, guys, let us know. We'll do a subnet workshop maybe next week or the week after that if you guys desire that. I'm going to continue the remaining 3 or 4 slides from subnetting, and then we'll ask you if you need it, and if you need it, we'll ask you, and if you want, we will get a subnet workshop scheduled because I want to make sure you're good. But there's only so many we can do while we're going through a course like this. So why do we subnet? Basically speaking, because I told you we were going to lose 16 million addresses for a single subnet. we would chop it into multiple subnets. So what are we doing? Subnetting is going to optimize our IP address space. What does subnetting really look like from a practical perspective? And it looks like you guys want a subnet class. I'll go make a subnet class. Anything we can do to give you guys a good experience and help you guys learn is fine. So let's say over here, we've got this class C address, if we want to use it, this 192.168.1.0/24. If I needed to break that down into multiple smaller addresses, I can create a network that has a 192.168.1.0/28 and a 192.168.1.16/28, and then a 192.168.1.32/28, and then I could do a 192.168.1.48, et cetera, et cetera, et cetera. So what subnetting is, it's taking one big network and breaking it down. So basically speaking, that's it. Now let's go back over here, and I made a little chart that I want you to know because it changes everything on the cloud. Please keep this in mind. So when you're with AWS, the smallest subnet you can use is a /28, which typically speaking would give you 14 usable addresses. 2 to the 4th minus 2, but and the reason what's to happen is we get 16 addresses, but what happens is the 192.168.1.0 is used for the router, and in this case, the broadcast address, don't know what happened there, of 192.168.1.15 would be there. So now I'm going to ask this, is everybody familiar with this on the subnet piece? If not, it looks like a bunch of people, we need a subnet thing. So so with AWS, they're going to use 5 addresses per subnet. So keep this in mind. AWS reserves the first 4 addresses and the last address. Why am I saying this? Why am I really concerned about you knowing that AWS uses 5 addresses per subnet? Here's the reason. If you have a /28 and you lose 5 addresses, which means you really only have 11 servers. And if you've got a couple of web servers, and you've got a couple of app servers, and you've got 2 load balancers, and something auto scales, you're going to run out of IP addresses. And if you run out of IP addresses, auto scaling stops. So if you run out of IP addresses, auto scaling stops. So I'm going to give you some guidance. The smallest subnet you should ever use for a LAN segment is a /24. Don't use bigger than a /23, and don't use smaller than a /24. Even if you think you need 10 servers, give yourself room for 253. You never know when you need them, and they're private IP addresses, and they're free, and they don't cost you anything. So give yourself a /24 for a subnet and /30 for WANs. But otherwise, /24 for a LAN, /30 for WAN. No bigger than a /23 for the LAN ever, because you're going to get too many broadcasts. Now, if subnetting is taking one subnet and breaking it down, we can also do the exact opposite, something called supernetting. So if I want to take subnet 1, subnet 2, subnet 3, subnet 4, and subnet 5 and make them look like a single subnet, I can do that. So why would I want to supernet? So when you're dealing with, AWS, you can only send them a certain number of routes. So let's say I connect my router to 3 different internet service providers because I want to create some really good internet connections. I run BGP to internet service provider 1, 2, and 3. My router takes in about 800,000 routes from each internet service provider. Got about 2.5 million routes in the routing information base, and 800,000 go into my routing table. That's a normal internet router, taking in 800,000 routes. When I send to AWS, they can't take more than 100 routes. Pretty common to have an organization with 200,000 employees that's got 40,000 subnets, 40,000 routes. AWS can't take more than 100, which is nothing, 100. So what do you have to do? You're going to have to be able to take your routes and make a bunch of little routes look like a couple of big routes to take the load to work around the limitations of the cloud provider. Look, it's not that the cloud providers aren't great at what they do. Think about this. If I connect to the internet service provider, I take in 800,000 routes. No big deal. From 10 internet service providers, that's 8 million routes. Look at Azure. Look at AWS. Look at Google. Look at 5 million customers that all have 40,000 routes. It's not going to work. So they have to make these trade-offs to make cloud computing possible. Remember, they're renting you access to their data center, so they can't break themselves either. So supernetting is the exact opposite of subnetting. Network architects like me use supernetting every single day. We take routes, we summarize routes, and we make the routing more elegant. And this, by the way you set up your IP addresses, and if you guys want, we can do towards the end of the week, we can do an IP addressing workshop and show you how to set up your addressing for the cloud. It's way, way, way above what you cover on the AWS Advanced Networking, but it's absolutely essential to actually be a cloud infrastructure architect. So if you guys want that, we'll happily do it. But I want you to understand that supernetting is you take multiple subnets and you aggregate them together. So let's look at what it normally would look like. So this is what route summarization is. Let's say we've got all these contiguous subnets, 192.168.0.0, 1.0, 2.0, and 3.0. These are all in our data center. Now, AWS only gets us have 100 routes, which is kind of nothing. 1, 2, this is 4 routes right over here. But if I take all these and create a summary address or an aggregate route of 192.168.0.0/22, all I need is to send that route to AWS. AWS can reach that. It can hit my router, and once it gets to my router knows, oh, send it over here versus send it over here. So supernetting or route summarization is really used to influence your traffic engineer your traffic, and remove routes from the routing table to promote scalability, performance, and availability. I hope that makes sense to you guys. And if you need us, we'll do a breakout session where we whiteboard it and design all this stuff together, whatever you guys need to be good, to get it completely, because I want you guys all rock solid. So now let's talk about IP addresses for a second. We've been normally using Ipv4 addresses. IP version 4 addresses have been around forever. And it's a 32-bit binary address. So if you want to know the available addresses, you can do 2 to the 32nd minus 2. That tells us pretty much exactly every possible IP address that we have. It's a good number of addresses, a couple billion, but it's not that many. Now, IPv6 is a newer form of IP addressing. Newer isn't like only 30 years old, but we don't use it. But it's getting used by mostly mobile phones. At some point, we'll be adopting it later to other things. So let's look at this so far. So it's a 128-bit hexadecimal address, which means 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, A, B, C, D, E, F. So 15 or 16 times 16 to the 128th power, that is your number of IP addresses. A lot. So infinitely more scalable than IPv4. Typically, mobile phones, all interfaces in AWS are given an IPv6 address. And there's no concept of private addresses because we don't have a problem running out of addresses. So here we go. I think we've covered this. Now I want to start moving into the virtual private cloud. So before we do, just want to make sure we're all level set on the addresses. We're moving on to the VPC. Looks like you guys want a subnet thing. You guys asked for a subnet thing. Chris from my team heard it. He is going to find a time to do a subnet workshop in the next few weeks. Everybody will be invited. So we got one very simple question I think we should answer. How do you differentiate a public IP address versus a private IP address? A private IP address will always be from the RFC 1918 address space. It will always be something in the range of the 10.0.0./8, the 172.16.0.0/12, or the 192.168.0.0/16. All private addresses are inside of that range. If it's not inside of that range, it's It's not a private address. But it's a great question there, Devonish. Okay, everyone, let's talk about the VPC. This is the fun. This is the cloud stuff. This is where we're touching the cloud networking. And tonight, we're going to have lots of fun with the VPC. We're going to be configuring stuff and designing stuff, and we're going to have a big, big, big party. So please join us. We love playing. So what is part of the VPC? Realistically speaking, we're going to be talking about routing and routing tables, internet gateways. We'll talk about egress-only internet gateways. We'll talk about NAT gateways. We'll talk about elastic IP addresses. We'll talk about VPC endpoints. We'll talk about VPC peering, network access control lists, and security groups. Okay, it just hit me. So it hit me. How many of you really know BGP? So if you know BGP, in the chat box type, I know BGP. If you don't know BGP, and we're going to need it for all the routing, let me know, and I'll do a quick Bgp brief or a quick Bgp brief, and then we'll go into it. So I want to know what you need, because you got to know BGP. There's no way to do any of this cloud networking without it. So if you want me to cover BGP before we do this, I will. If you don't want me to, let me know. So just let me know. It's looking like most people have said they don't know BGP and you're here to learn. I will do some BGP. Realize it's going to take us about 45 minutes to get back to this stuff, but we've got one person that knows BGP, two people that know BGP, three, please cover, don't know, cover. Okay, we're going to have some fun with BGP. Let's talk about BGP, or the Border Gateway Protocol, which is one of my absolute favorite protocols. I've got well over 10,000 hours of experience in BGP, and let's talk about it. The first thing that I want you to all know is in your VPC. Yeah, Aqua, I would assume you do with your background. Fantastic. So inside of your data center, you're going to have a routing table. The routing table is the map that teaches you how to go from point A to point B. That's the map. So if you've not seen this, it's going to look something like this in your cloud provider. You're going to have a table, and it's going to be a funny looking table. And inside of here, I want you to see this. I've drawn a manual routing table. I've got a 172.16.1.0. I've got a 172.16, and the target is where you're going to send your traffic to reach that. I've got a 192.168.1.0/24 and a 0.0.0, which is a default route that points to my internet gateway. I want you to look at this. Really, really important. See this 172.16.0.0/16? And this 192.168.0.0/16 and the 192.168.1.0/24. 192.168.0.0/16 contains the 192.168.1.0/24. It contains it. But look very carefully. You can see that the aggregate, or the /16, points to one interface. Oops. And you can see that the /24 points to another interface. The virtual router in the VPC or the router in the data center, it doesn't matter, will say traffic destined to this 24 goes here. Traffic destined for anything that doesn't match this in this range go here. So what routers do is they look for the most specific route. The most specific route. That's where they go. The most specific route. So when we're tuning things, we're going to talk about tuning things next. And we're going to have to put our propeller hats on, because BGP is the most complicated routing protocol of all of them. It's the one that 99% of all network engineers don't even know. So we're going to have to put our thinking caps on. But I want you to understand this. So let's do a brief BGP overview. So why do organizations use dynamic routing protocols? I want to make it very clear. When you connect to the cloud, you're going to have two options. Option one is let's say you have a VPN, you could put static routes. You manually put a static route. Here's what a static route is. Any of you want to go to your friend's house that lives 2,000 miles away, you go to your computer, you print out directions, and you leave your house. Now, somewhere along the line, a road's blocked, you're stuck. You don't know how to reroute around it. You only know how to go left here for 100 miles, go straight, and that's your dynamic. It's an old-fashioned map. By comparison, what if you had a GPS in your car that could see the roads closed and recalculating, rerouting? That's what dynamic routing protocols do. So organizations have two kinds of routing protocols that they use. Organizations have what's called interior gateway protocols and exterior gateway protocols. So let's look at it. Inside of the AWS network, Amazon themselves, they're running an interior gateway protocol. I can tell you it's either OSPF or it's intermediate systems to intermediate systems. That is their IGP for their organization, for all their data centers. Now, that's what they use internally. Interior gateway protocols are used inside of organizations to find the fastest routing to get your data from point A to point B. That's what interior gateway protocols do. Now, by comparison, interior gateway protocols are used for an entity. Exterior gateway protocols are used to connect to entities. So if you have AWS on the right side of the screen and your data center on the left, you're going to be running an interior gateway protocol for all your stuff in your data center to talk to each other. AWS inside of their cloud is going to be running their OSPF to make sure their network is up and running. But you don't connect to AWS with OSPF or intermediate systems to intermediate systems. You connect to them with regards to BGP. BGP is an exterior gateway protocol, which is used to connect you to external entities. So this is what it's going to look like. You'll have your data center, they'll have their data center, and you'll use BGP to connect to AWS. That's why we're covering BGP here. It is the most critical routing protocol when it comes to cloud computing. And the reality is, and the saddest part of this is, there's probably 1,000 people in the whole world that know BGP, and they're all network people. And for the most part, almost nobody knows it. I want you to know it is a really important thing. So BGP is an exterior gateway protocol. Why do we use it? To connect to external entities. As I mentioned, routers build a map of the network, and they use routing protocols to build the map of the network. To get to this destination, go out the right arm. To get to this destination, go out the left arm. To get to this destination, go downhill, uphill, sideways. Routers have a bunch of ports on them, and that's how they know to send their stuff based upon the map of the network. So routing pros do it. Inside of organizations, we use interior gateway protocols, OSPF, EIGRP, intermediate systems to intermediate systems. In between organizations, we use an exterior gateway protocol, most notably BGP. BGP is used for the following reasons. It scales like you can't imagine. 750,000 routes, 10 people, we use BGP. BGP allows for extreme tuning. If you read the book, Internet Routing Architectures by Bassam Halabi, and I encourage everybody to do so, there's about 400 pages of different ways you can tune your training, your traffic to go to the right place. About 400 pages of different ways to tune your traffic, and that's just scratching the surface. So highly scalable, highly tunable, lots of traffic engineering. Now, when you're using BGP, I need you to remember this. It's unicast. Every other routing protocol, almost for the most part, identifies each other with hellos that are multicast. BGP is unicast, which means sent directly from one user to another, unicast. Not one to many, one to one. Now, test question here. Ding, ding, ding. You're going to see it on an exam. TCP, our BGP uses TCP port 179. TCP-based port 179. Yes, you will see that on an exam. Why do I care? Not for an exam, because you're going to be dealing with firewalls. And you may have to allow TCP port 179 through your firewall. If not, your whole network will break. So BGP uses TCP port 179. Know it, know it, know it. It is essential to know this. So let's talk about how it works. So BGP and all these protocols are algorithms. And let's work through the algorithm. Now, this sounds like surgical torture, algorithm work. And you know what? It's a little ugly, But when you know the algorithm and you know how to tune the algorithm, wow, what kind of cool stuff you can do when you can tune the algorithm. So when we're going to talk about BGP, we have to talk about the finite state machine and the 4 messages, and then we tune and traffic engineer. That's where the magic happens. And so let's talk about the 4 messages. There's going to be an update, an open message, a keep alive message, an update message, and a notification message. So let's go talk about the open message and what it is. So let's say you've got 2 routers. Remember, TCP port 179. So what's the best thing they do? TCP port 179, you send an open message. The open message says, hello, neighbor. I'd like to form a relationship. I'd like to start exchanging information. In that open message, they talk about their BGP version, 3, 4, what have you. They identify your autonomous system number, which is what identifies you on the network. And they come up with, they exchange their parameters, such as like their hold timers and their BGP identifiers. Open says, hello, sir. Hello, ma'am. Please form a relationship with me. I'd like to start a conversation and exchange routes. That's what the open message is. Then there's something called a keep alive. I don't know how many of you guys are familiar with health checks when it comes to DNS and load balancers. If you're not, by the end of the week, you're going to be an expert. So a keep alive is like a health check. Basically, you've got one router sending a message to another router. Are you there? Are you there? Are you there? And this guy says, I'm here. I'm here. I'm here. This guy says, are you there? This one doesn't respond. This guy says, are you there? Doesn't respond. It's like, are you there? It assumes the BGP neighbor is dead. It tears it down. Kind of simple. Just like, where do we see something like this? Where do we see something so simple like this? We see it with a load balancer. We see it with DNS. Health checks, they're everywhere. Where do you think these health checks came from that we're using 30 and 40 years later with us? From the networking. So open, hello, let's have a conversation. Keep alive, I'm here, are you there? Are you there? So let's keep going on. Let's work through this. And update information. Okay, I've got my neighbor relationship. We shook hands, we're friends. I say I'm alive, they're alive. The keep alive is not ICMP, SM7. It's part of the BGP protocol. It is a BGP open message, which is TCP based. I'm saying it's a keep alive message, which is TCP based. So now I've learned a new route. I want to tell my BGP neighbor, I send an update message, or a route went away. I withdraw the route. So an update message basically says, pull a route, do a route, or information about the route. Now, the last kind of message is a notification message. So if an open message is, hello, let's have a conversation, and a keep alive is things are good, and an update is when you want to remove something or add something, all those things are good. A notification message is not a good thing. A notification message is when your wife calls you to yell at you because she's mad at you for doing something stupid. So a notification message basically says, there's a problem here. We're going to tear down the connection. There's been an error that's detected. So notification, not so good. Open, let's form a relationship. Keep alive, I'm alive, you alive, let's continue our dance. Update, something changed. Notification, we got a problem. Houston, we have a problem. So now let's talk about how these guys form their neighbor relationship. Now this and next the attributes are gonna, which I know are a little heavy. I got my geek hat on. I got both propellers spinning really fast, but we got to know this, and it's part of the architect's job. So there's going to be a couple phases we need to talk about the neighbor relationship. So we'll talk about the idle phase, the connect phase, the active phase, the open sent phase, the open confirm phase, and the established phase. And for all of you who've got much deeper BGP training on this YouTube channel, if you need, and if you guys want more, I'm always happy to play Mr. BGP. So when you first turn BGP on, the routers are in what's called an idle state. They're looking for a TCP connection. And if the 2 routers form that TCP connection like we talked about before, when the open message is sent, the BGP speaker transitions to open sent. This means everything is good. Oh, wait, what if that doesn't happen? What happens if we try to connect and all of a sudden we send that open message and it doesn't go through to the neighbor? We transition to an active place. Active is a bad place. Active basically means we're going to try and reestablish a connection. I'm going to get out of this as fast as I can, everyone, but I want you guys to be able to get it. Then Assuming I go from open to open send and everything is good, the far end router will say, I got your open message. Now I'm going to send you a keep alive to know that I'm here so you know that I exist. And then once the keep alive gets sent, it transitions to something called open confirm. When we hit open confirm, realistically speaking, this means that a message was sent and received between the BGP neighbors. When that occurred, both BGP speakers come up and they reach a state called established. Established means the handshake's been completed. Router 1's now a BGP peer. They're now good buddies. They're great buddies. They're exchanging routes and everything is good. We want to see established. So let's briefly talk about attributes. Then we'll get into the fun part, which is the architectural tuning of it. And then we'll go back to the AWS VPC. But at least we gave you guys some networking fundamentals, which I think are really, really important. So let's talk about the BGP attributes and what they are. There's going to be an attribute called the origin. The origin is just how you learned about the route. Did you learn about it because it was inside of your interior gateway protocol, which would be the best? Did you learn about it through BGP? Where did you learn about it? You don't know how you learned about it, which is called incomplete. So the next thing is regards to the path. I'm going to get out of this really fast, guys. Bear with me for 5 minutes to get through the BGP so we can tune it. So how do we learn the routes? Every time the routes go through an autonomous system or a company, what happens is they get prepended or they add it. They add it. So what'll happen is we'll work through this. The path will show how far away it is. Then we'll talk about the next hop, which is where you go from one router to the next. And we'll work our way through this. Then there's a parameter called weight. The higher the weight, the more preferred the path is. So let's talk about the path selection process. Then we're done. Then we're going to just talk about how to tune it. So I need you to all understand this. This is the perfect interview question. I ask this to everyone. And if somebody doesn't know this, I can't hire them ever. Everybody I deal with is. So the path is prefer the path with the highest weight. Next, prefer the path with the highest local preference. If the local preferences are the same, prefer the path that was originated locally on the router. If the origination of the routes and the local preferences are the same, take the path with the shortest AS path. If the AS paths are the same, take the one with the shortest origin code. Then, if the origin codes are the same, prefer the path with the lowest MED. And then prefer eBGP routes over iBGP routes. And then it gets really stupid, so I don't even want to go there. So let's walk through a couple of situations. And let's just kind of walk through so we can look at it, and then let's get into some of the AWS more specific stuff. Let's take this particular environment. Let's say you've got an organization and on the right, and you've got a data center. I've got to make sure that we give you guys access to the actual subnets. I don't know how I'm going to do this somehow. Okay, let's do this. Bear with me.
Make the image smaller.
Make the image smaller? Excellent idea.
Yeah, so click, yeah.
Okay, excellent. Can you guys, oh, that's perfect. Thank you. So let's go into this environment. Note, I have two links between AWS and the data center. Two connections. Now, I've got options. And the reason we're talking about this, and we're going to talk about it more later, but the reason we're talking about this is as follows. If this connection and this connection are what's called the same cost, meaning in the routing world, it's the same distance to go from here to here as it is to here, and in most cases they're going to be. What'll happen is you could send your data from the data center over the top link, and your data could come back on the bottom link. So what could happen is you could be leaving the top, going to across the top link for your data sent, and half of your data can be coming back on the bottom link. Now, let's be fair. If I send you data to your house on the highway and it comes back the same highway, it's great. But if I send you some data and some of it takes a turnpike and some of it takes I-95, the problem is your traffic is going to get back at two different periods of time. So realistically speaking, anytime you're going to have two direct connections to AWS or any kind of redundant connections, you're going to have to do something about it. If you don't do something about it, you will have a problem. So if you just get 2 direct connections from AWS, expect problems unless you deal with the BGP side of it, which is why I feel like you can't ignore BGP in an AWS Advanced Network course. You will have problems. What'll happen is, let's say your traffic will go out the top link and then come back to bottom link. So I want you to understand the nature of the problem. Nobody buys both of these links, the top link and the bottom link, from the same service provider, because it would be crazy. If you put all your links in if you put all your links in AT&T and AT&T has an outage, both links go. But if your top link is with AT&T and your bottom link is in Verizon, if one of your routers dies or one of your internet service providers dies, you're still in good shape. It doesn't matter. So what organizations are all going to do is they're going to have a connection and they're going to have a backup connection, but they can't have their data going on one link and coming back. So you've got 2 options for traffic engineering. Option 1 is to block one of the links and it'll only come in on backup. You can do that by making one link look ugly. Option 2 is you can intentionally load share. You can intentionally send one subnet on the top and one subnet on the bottom. And if either link will go away, then what you would actually do, realistically speaking, like if the top link were to go away, you can send the traffic on the bottom link. So what I would do, and this is what I've done here, is if you can see very carefully, on the top link, I've sent a specific route to the 172.16.0.0/16. And on the bottom link, I sent a specific route to 172.17.0.0/16. I've pre-programmed that. Now, if the bottom link goes away, don't worry, I've got the top link and the top link and the bottom link. Now, I also put this aggregate route or this summary route of the 172.16.0.0/15. That, by the way, enables me to have reachability should one of the links go. So the easiest way to load share without getting out of order packets are to do as follows. Send specific routes on one link, more specific route, another specific route on a different link, send a summary route, and that way you're load sharing across both and you don't get out of order packets. That's the easiest and most elegant way to do this. But it's not the only way to do this. The next option that you have is if you wanted to influence the direction that you're sending your traffic, and mind you, you have to do this in both directions, in and outbound. I'm just showing you one direction to make it easy so it doesn't look ugly. What you can see here is on the top link, we've made 172.16 more preferred. And on the bottom link, we've made 172.17 more preferred. And the way we did it is as follows. What we ultimately did over here is prefer the path with the highest weight. So note, I took 172.16.0.0 and raised the weight to 35,000. I then took 172.17.0.0 on the bottom link and raised that weight to 17,000. So then what I did is I took those subnets that I didn't want to be used and I reduced their weight or gave them the default weight. So if you can see what I did here, I made the weight higher from one subnet on the top link. I made the weight higher for a different subnet on the bottom link. And in the process of doing all of this, I'm load sharing without getting out of order packets. Again, this is what every internet service provider does. This is what network architects like me do all day, every day. Every time we've got multiple direct connections to a cloud provider, this is what we do. Now, remember what we said, prefer the path with the largest weight, prefer the path with the largest local preference. So option here again, we raised the local preference from 100 to 200 to our specific route over here. We then raised the local preference for a more specific route over here, and then we keep the default for something else, and now we've, again, load sharing without out of order packets. Let's do it another way, prepending the AS path. If you'll recall, I told you every time you traverse an autonomous system, it adds. So let's look at this top link. So let's assume this path, or this autonomous system that we're talking about is 64523. So if it learns the route 172.16, it's learning the path via 64523. But look what I did to 172.17 to make it look ugly. I added an additional 64523 path. That's called prepending or AS path prepending. What did I do there? I just did it. Why did I do it? I want this route to be more attractive than this route. So that's why I did that. This route, again, will be more attractive because it's the shortest path. And like I said, we could have tuned the med too. Of course we could have tuned the med. Prefer the path with the lowest med. I want this route to be preferred. I gave it a lower med. I want this route to be preferred. I gave it a lower med. That's why we're using BGP, everybody. That's why we use BGP. So we use BGP for the following reasons. It's tunable. It scales. So when do you use BGP with AWS? Now that we're getting into the fun part of the VPC, anytime you have a direct connection, you're using BGP. Anytime you're using Cloud Hub, you're using BGP. Anytime you want to do dynamic routing, you're using BGP. So the real thing is, when are you using BGP in the cloud computing environment? Everywhere. So, if we have to, we'll do more BGP training for you guys at some point. But BGP training is everywhere. So when you're dealing with AWS, it's got a very limited BGP implementation, but it does support the key things: weight, local preference, AF path, specificity of routing information. So you can use it exactly like what we talked about. Okay, everybody, let's talk about some AWS stuff. Let's start with an internet gateway. Woohoo, we got into the AWS stuff. Now the fun stuff. But wanted to do those fundamentals. So let's talk about internet gateways. Everybody type internet gateways in the chat box. We'll talk about internet gateways. So what is an internet gateway? An internet gateway right now is simply a router that connects to the internet. That's it. An internet gateway is a router that connects to the internet. If you want to connect to the internet, you need an internet gateway. That's it. In a data center, when you connect to the internet, you have a router that you buy a WAN connection to the internet. What do you do in the cloud? You get an internet gateway. And it is a virtual router with a virtual connection to the internet. That's it. Now, when you're dealing with the AWS Internet Gateway, they like to say that there's no bandwidth or performance constraints. So they're going to tell you that it scales, it scales, it scales. Just remember it this way. You get an internet gateway. It's a router that connects your VPC to the internet. Don't make it so complicated. So while we're at it, let's talk a little bit more about internet gateways. Here's what you do, how you set it up. The internet gateway is created in the following manner. You attach an internet gateway to your VPC. You put a default route on your systems that says send all unknown or 0.0.0.0/0 traffic to the internet gateway. You put a public address on your internet gateway, because remember, it's going to be on the internet, so it must have a publicly facing address. And that's it. You're on the internet. Now, okay, this is real internet access. If I connect me to the internet, and I'm now on the internet, I'm here on the internet, what's going to happen to me? I'm going to get hacked. So the second your systems are on the internet, they will be hacked. So internet gateway gets you straight to the internet. Now, if you're on the internet, you're going to need firewalls and IDS, IPS systems and the whole gamut to protect you. So please understand that you need that to protect you. So we're going to have to talk about security when we do these kind of things. So let's realistically look at what this concept of an internet gateway really is. So in this particular environment, and let's say we've got to move this stuff over, what we have here is we've got an internet gateway that's connected to the internet. The internet gateway is really a router. We're separating the router because we're using the logical VPC router. And what you can see is your instances that basically have a network load balancer that has an external IP address, which is on the same subnet as the internet gateway. So basically, that's how your systems will be reachable from the internet. Internet gateway will be here. You'll have a load balancer that'll front end your servers, and the external end of the edge of the load balancer will have a public-facing IP address. That is an internet gateway. Are we ready to keep going, or do I need to stop, take some questions for 10 minutes before we cover the rest? You guys tell me if you're good to go from internet gateways to egress-only internet gateways, let me know. If you guys need to ask some questions, let me know. I can't tell because we're on YouTube, so instead of Zoom, so I can't see your faces, so I don't know. But if you need me to stop for questions, great. Otherwise, we'll go for about 5 or 10 minutes more. Abigail, you got some questions? Ask some. Let's see what everybody says. I'm going to keep going until we get some responses, and then Chris is going to tell me what to do. So let's actually, we're starting to get some real questions. Let's do some questions. Some of these questions are starting to feel pretty real. Dimitri, it is clear how traffic routed inside the VPC, how to find the Dimitri, it is clear how routed traffic inside. I'm not really sure I understand the question. How does the traffic find your VPC, Dimitri? Well, ideally, traffic would not find your VPC at all. All the systems on your VPC would be private and connected internally to you and your systems. Nobody should find it. What should happen is on your data center side, you've got a router that's plugged into it's got a direct connection, for example, to AWS. Between BGP, you exchange routes, and all the systems inside of your data center know exactly how to reach in the cloud. And because you've exchanged BGP with the cloud provider has routes back to your data center. That's the way it should work in a normal world. Now, how will it find your websites, for example? That's easy. Your DNS provider will point to your external-facing website or your load balancer or your content delivery network. So that's how traffic outside is going to find you. Inside your VPC, your traffic's going to know exactly what to do because it has a virtual router. And the virtual router will build a routing table. That's how your traffic inside your VPC works. Pierre, does a network load balancer face the internet before the router? You've got the router. Behind the router, you've got the front edge of the network load balancer. And then behind that, you've got the servers, Pierre. What is the maximum internet bandwidth supported by AWS? You'd have to call them. It changes constantly. And just because they have a standard bandwidth, that can then change after you request specialty services above. So you got to call them. Okay. I didn't see Chris pop any more up there. So let's go back to the egress-only internet gateways. So I had previously talked about internet gateways, which provided real internet connectivity. And what I mean by real is I'm reachable from the internet and I can go to the internet. Reachable from the internet, go to the internet. That's real internet access to me, bi-directional. Go to the internet, come back from the internet, go to the internet, come back in the internet. So, but what if I wanted egress only? So let's talk about egress only now. I'm right now sitting inside of my house behind my firewall. I don't need anybody to reach anything inside of my house for any reason whatsoever. None. Well, some people have to reach my DMZ to get into some of my clouds to play around, but nobody needs otherwise to get behind my firewall in my house. No one. So I'm firewalled off right now. But inside of my subnet where I'm sitting, I've got 9 24-core servers. The little geek in me comes out every once in a while, and I like to experiment. I've got my system, which is a 32-core Threadripper system that I'm using right now. I don't want anybody accessing my systems. I've got video encoders. I've got cameras, and they're all sitting behind the firewall. Many of these devices I'm talking about may need to be patched for vulnerabilities. I'm in a thing that's streaming video. So guess what? I've got my tray comes back to the internet. I've got to send video to YouTube. I got to be able to see things. So I need to be able to go to the internet, let my traffic come back to me, but I don't want to be reachable. So that's what's called egress-only internet access, meaning I can reach the internet to pull stuff and come back to me, but I'm not reachable from the internet. So this is really something special. So this gives you security and internet connectivity at the same time. So good stuff. So an egress-only internet gateway, that's what it is. Now, In the context of AWS, an egress-only internet gateway only works for IPv6. A NAT gateway, which is also an egress-only internet gateway, has a different name. Egress-only means out and back. So in AWS, an egress-only internet gateway, according to their terminology, is only for IPv6. Remember, all IPv6 addresses are public. There's no concept of private addresses. The egress-only internet gateway lets my IPv6 traffic out to the internet and return, but it does not allow anyone to reach into me. That is called an egress-only internet gateway. Now, let's say we're using IPv4. We want to go out to the internet to update the operating system on our systems. Guess what? We have a couple ways we can do that. We could use a NAT gateway, which is something we'll talk about, and we could use something else that's not a NAT gateway. We could use something else that's called a NAT instance. So let's talk about the two options. First, we're going to begin with NAT instances. Now, when I talk about NAT instances, what we're really talking about is a system, an EC2 instance, a computer that's going to translate one address to another address. That's what NAT does. It translates one address to another address. Now, NAT to me could go from one company to another company. NAT does not have to be to go to the internet. NAT is translation of one address to another, and that's it. That's what NAT means. But a NAT instance in AWS is used to give people egress-only internet access. So what happens is you set up a NAT instance, and I'll graphically show you what it is, and then you point the NAT instance to the NAT gateway. And what happens is the NAT instance enables egress-only internet access to the hosts that are using that NAT instance, while the NAT gateway, while the internet gateway provides true internet access to the NAT instance. So let's see what this looks like architecturally speaking. Here you've got the internet. Behind the internet, you've got your internet gateway, which is your internet router. You've got your NAT instance, and you've got your private subnet. So all these servers that are behind the NAT instance, they can go to the internet to update their operating system, but they won't be reachable from the internet because it's egress only. Let's talk about one more kind of NAT with AWS, and we'll call this a NAT gateway. What's a NAT gateway? Well, a NAT gateway is a fully managed NAT service. So we just looked at a NAT instance where you needed an internet gateway and then a NAT instance. And NAT gateway is kind of this all-in-one kind of concept. It's a fully managed NAT service. It's high availability, meaning it's not going to go fall apart because it's a logical device. But you need one per AZ, per availability zone. What you do is they create a NAT gateway in a public subnet. It has an elastic IP address, and you give everything a default route to the NAT gateway. And then everybody goes to the internet, and everything works great. Let's look at this situation over here. It's really kind of cool. Got our servers and a private subnet. They're not hackable. They're not reachable from the internet, but they can go out to the internet, update their operating system, and be done. That's what a NAT gateway does. So now so before we go over, let's do these NAT things one more time. Egress-only internet gateway, IPv6, go out and return, but not reachable. NAT instance plus internet gateway, egress only IPv4 traffic. Go out, allow your return traffic back, nothing else. Okay, so next on the list, NAT gateway. Single device has an internet gateway and basically a NAT instance all on a single device, allows your traffic out to the internet and it comes back. Now you know the three. So let's talk about Ethernet cards and network interfaces. Every computer that we need has to get plugged onto the network. If we don't plug it on the network, you can't use it. It's not reachable. So what does every computer need? It needs a network card or a network interface. So when we're dealing with networking and we're dealing with servers, they're going to have a network card, realistically speaking, inside of our systems. Now, when we're dealing with a physical Ethernet card. When we're dealing with the cloud, we're dealing with virtualized everything. Virtualized everything, which means your network cards are going to be virtualized, and they're going to be called an elastic network interface. Now, an elastic network interface is a virtual interface. Remember, there is no such thing as physical in the cloud. It's not like I can stick a firewall in Rocket. It's not like I can stick a physical router in there. It's all virtualized stuff at the cloud provider. So when you start your system, it's got one. It's going to be called ETH0. That's going to be your default, elastic network interface. But there are times where you need to put multiple network cards in a server. Maybe you want to put a server in 2 different environments. There's lots of reasons you could do it. There's some kind of really horrible, monstrous, scary, dangerous best practice for thing that you'd never want to do, a security violation called a bastion host or a jump host, where you leave this widely exposed system on the internet and you've got another network card and you can use it as a backdoor in your internet. I would strongly recommend against that, but that's a perfect example of why people will do this. And if you guys want, we can have a session one day and talk about all the good reasons you would never do a bastion host in real life from a security perspective, because you could talk about that for hours of why that's such a bad idea. But a bastion host would be a perfect example of a dual home server. Another example of a dual home server is if you've got finance users that are on it and somebody else, and you don't want them to go through a switch, you could put multiple network cards. So for speed, sometimes servers have multiple network cards. AWS calls a network card an elastic network interface. Now, if an elastic network interface is a network card, we need to put a public IP address on anything that needs to be reachable. So somehow the people at AWS love the word elastic. So they decided that they would call a public IP address an elastic IP address. So what is an elastic IP address? It is a public IP address that you borrow from AWS. A public IP address that you borrow from AWS. You keep it as long as you need it. And then when you're done with it, you return it. So with AWS, you get to rent or borrow their IP addresses, and they're called elastic IP addresses. Elastic network interface, network card. Elastic IP address, public address. So let's look at this. Let's look at this environment one more time. We've got the internet. We've got our internet gateway. We've got our virtual router that maintains the routing table of your VPC. We've got your elastic IP address, which is the front end, which is probably sitting on a network load balancer in front of your web servers. And poof, everything's on the internet. Everything is working awesome. Everything's working awesome. So the next content that we're going to get into are VPC endpoints, which are one of my coolest things. What a great way to securely connect to a bunch of endpoint services. Really cool stuff. Lots, and lots of fun. So while we're at it, everybody, let's see if there's any questions. It looked like a bunch of questions were coming in. Some of them look like they really needed to be addressed. Some of them may cause me to do some additional workshops if you guys desire. So Chris, I want to bring in some of these questions. I don't want anybody to have anything other than a great experience. Shishir, Azure does not have the concept of an internet gateway and a route table. Well, there is a concept of a route table, but it's more hidden from you. You have the traffic open on Azure Virtual Network. Why is Microsoft kept it? It's not exactly open on Azure. When you really look at what you have to do with the Azure and your VNet, what basically happens is everything's basically connected to the internet if it's got a public IP address in it. They've done all of the work for you to make it a lot easier on you. A lot easier on you. So it's just that. When would you use a NAT instance and a NAT gateway? I can't think of any use case why you would use a NAT instance in today's world, given that the NAT gateway uses it. Realistically speaking, anytime you've got systems that need to connect to the internet, you're going to use a NAT gateway, which is pretty much 100% of the time, Aniket. If you've got a server that needs to be updated so that it doesn't have security vulnerabilities, you will need a NAT gateway. So basically, any use case is every time you ever connect to the cloud, you're going to need to make sure your servers can be updated, and you're going to need a NAT gateway. But a NAT instance, you're probably never going to use. And is a NAT gateway a physical device like in net routers and switches? No, these are logical devices like routers and switches. So realistically speaking, they're logical devices. So Think about it this way. AWS built a really cool router that doesn't go anywhere. So, it's not like if it's going to crash like a physical router, it's a logical device. So, when we're dealing with some of these cool things in the cloud, having these devices being logical isn't necessarily a bad thing. It's a really great thing. So high availability logical devices, we love that. Chris, if you want to bring in the next question. Ken Sherman, may you turn the tables. What questions do you have for us? You're open for a quiz right now to celebrate the Cerebral Juices. I can't really ask you guys any questions. It's not like you can respond to the questions. I mean, I'm more than happy to try and ask some questions. Actually, I can try and ask some questions and see if you guys get it. Okay, the first one. Where does this subnet start? 192.168.1.2/30. Where is the 0? Where is the broadcast address? And which 2 addresses are usable? Somebody can type it into the chat box. Yeah, actually, I don't think this is going to work.
Yeah, while we're waiting on people to respond, I'll bring up the next question for you.
Apostolis, echis polio onoma, and I have a feeling you understand what I'm saying with that. AWS has millions of users. Absolutely, they have millions of users, and that's why, with their excellent capabilities, they have to be smart about how many users they take and how many routes they take, because it would be impractical for anybody to not be smart the way they do it. So if AWS gives multiple IP addresses to their users, wouldn't they run out of public addresses? They've got a fair number of public addresses. When you're one of the world's largest internet service providers, you can get a fair number of addresses. And they also have IPv6 addresses, but you have to be fair. AWS, they're extremely smart, and they're extremely good at knowing how to judiciously use their addresses. Extremely capable. So I may make jokes about, marketing terms because it makes it hard for students to learn them. Every cloud provider, one uses Elastic, one sticks cloud in front of everything, but they're exceptionally good at what they use, and they have millions of users, but they do have addresses. So.
All right, here's some answers to the question.
Okay, so, well, Ankit is right, but he missed the router one, which was the .0. The first and the fourth, the first address is actually used for this subnet. The last address is actually used for the broadcast. 100% completely agree. And the .1 and .2 would actually be used for networking. Good job, Jeannie.
Yeah. All right, I'm going to pop a couple more questions up on here.
Excellent. What is the nth difference between a NAT gateway and a NAT instance? The NAT instance is an older device that's typically not used, and the NAT instance requires an internet connection, where the NAT gateway basically does NAT and it's connected to the internet. I got to give AWS a hand on that NAT gateway. It is a very simple, elegant solution. Just add a NAT gateway, connect to the internet for egress-only traffic. Very intelligent, very elegant, very simple to use. How strong is the EC2 anti-DDoS? Well, it depends on what your needs are. When we start getting into these really complicated architectures and really complicated security environments, you have to look at whether you're going to be using these cloud-native services or whether you're going to use marketplace services. In many environments, we can get away with some of the things like the WAF and the Shield. They're pretty awesome. In other environments, we're going to have to use things like Shield Advanced, and then we're going to go to the marketplace, and we're going to be using gateway load balancers and network load balancers to load balance across next generation firewalls, maybe some IDS, IPS systems. So it's all based upon what you need, Dilo. Sometimes the cloud native services are enough. Sometimes we need to bring in some enterprise services. Sometimes we can hybridize them. Sometimes we'll use like an Elastic load balancer to front end some F5 load balancers. There's all kinds of cool stuff that we're going to do and talk about, Dilo. All of them are appropriate. It's just a use case. So when it comes to me, I typically deal with organizations that are dealing with big, massive architectures. And for me, typically the DDoS prevention that I'm dealing with is about 6 or 7 layers. We're dealing with, something like a a shield on a content delivery network, which is awesome, and typically some gateway load balancers, some enterprise-grade firewalls from the marketplace, some IDS systems, some network ACLs, some security groups. Then we'll be dealing with some host-based firewalls and disabling unnecessary services. So it's going to be a lot of it. So realistically speaking, it's going to be based upon the requirements of the solution. The technical requirements will determine which service we choose.
All right, and I'm going to bring a couple of more questions in, and then we're going to get back to the content.
Abraham, is an internet gateway similar to a router? Abraham, an internet gateway is exactly similar to a virtualized router with a connection to the internet that's doing that. Exactly the same. Great question. And that shows some good understanding.
And that was actually the last one.
Okay, so let's talk about some more AWS fun stuff. Let's start talking about endpoints. And their work on endpoints is really cool stuff. So, when we talk about things, before we get into endpoints, I want to talk about performance. And I want to talk about like AWS network performance or Azure network performance or Google network performance compared to internet performance. On the internet, you've got a bunch of internet service providers that are glued to each other with BGP. Glued to each other. Now, that's the way the internet works. But here's the thing. Remember I showed you the routing and I said it was like a hot potato. You go from router to router to router to router to router to hot potato, send your data. Well, that's the way the internet works. There are no guarantees across the internet. Now, if Amazon owned the whole internet, Amazon could control the network. But they control their network. Traffic on the internet is best effort. There's no guarantees. Traffic on the AWS environment, by comparison, is guaranteed. They manage the network. They run the network. They optimize the network. They need QoS. They can do it. They control their network. So let's start looking at the performance of these kind of cool things. So AWS manages the network. So let's say you want to connect to an external service like S3. If you can do it over the AWS network, you can get there better, faster, and cheaper than if you had to go to the internet. So we're going to talk about endpoints as a means to securely connect to another service or organization in, in the AWS environment, leveraging the AWS high performance network instead of using the internet, which is insecure and also has no guarantees. So realistically speaking, that's what these endpoints are. And these endpoints are awesome. So I want to walk you through what it looks like. Let's pretend we do it with or without the endpoint. So over here, we've got our VPC. We've got AWS S3, great object storage environment that we can talk about. So between our VPC and our object storage, we have two options. We could go out the internet over an internet gateway, send our data across the internet, and then bring our data back into S3. Now, that's an option. Now, why isn't this a good option? First, we're now going to ride the internet, which has got poor performance compared to AWS's high performance network. And we got to go pay to send our data to the internet across only to come back in. So now we have less security and we have to pay for it. And we have lower performance because we're riding the internet. By comparison, what if we could just take the AWS private network directly there and basically create like a fake wire, like a logical wire, call it an endpoint, do it securely on the AWS network and have all the advantages of AWS's control of the network, their performance. Now we're dealing with something pretty good. So look at that. Now we're taking advantage of the AWS network, which they control. And they've got rock solid network engineers and rock solid connections. And they've got some of the biggest, baddest routers and switches in the world. Some that they had a custom build because the service providers don't even make them that performance. So think about the benefit of being on one of these networks. You're not on the public internet. You're riding a secure network at greater performance at a lower cost. That's why we love endpoints around here. So when we talk about endpoints, we're dealing with two kinds of endpoints. The gateway endpoint and the interface endpoint. So let's talk about what these endpoints are and when they are used. Gateway endpoints are basically speaking high speed, high security access to AWS services. And I love the way they work because they make sense to me. They place a route on the routing table. You're a CCIE with 25 years networking experience. You like routes and routing tables. So that's the way it works. So let's think about an Amazon S3 endpoint. Basically, it's going to give you private access to S3 from your VPC across the high performance network. Basically speaking, you're going to create an endpoint and from a prefix list. Basically, the prefix list will have a naming convention like a PL dash, whatever, and you'll see it in a routing table. I'll show you in a minute. So you're going to route in a routing table for S3. And what's that going to look like? You're basically going to have your data center, which is going to have a router. Let's say you've got a VPN to AWS. In your AWS environment, you're going to have a shared service. You'll have a load balancer set up with some proxy farms with a VPC endpoint going to your bucket. So realistically speaking, let me walk you guys through this one more time. I may not have been sharing my screen when I did this. Oops, didn't mean to do that. So what's going to happen over here is you've got your data center connected via VPN to AWS. Oops, let me just try to figure out how to make this smaller. Okay. So you've got your users, you've got your VPN, and what you can see is you've got a what do you call it, an endpoint that's going to connect to the bucket. It's going to put it to the routing table inside of your VPC, and that's how your systems are going to reach it. So let's talk a little bit about securing it. Now, this is one of those situations where routing security is kind of the best. Because the gateway endpoint uses routing, we've got a little bit more creativity. So if you limit routing to the subnets that need it, people that don't need it won't be able to reach it. So, when we start talking about security, we've got IAM, which is when somebody knocks on your door and says, I'd like to come in. Am I allowed? And the answer is yes, you are who you say you are. You're allowed in. You're allowed to sit on the sofa. And I've tracked you. That's your IAM. But with networking, if you don't have a route to it, you can't hack it in the first place. Thank you so much, Ilbra. If you don't have a route, you can't reach it. If you can't reach it, you can't hack it. So with gateway endpoints, you can actually limit the routing information. And by limiting the routing information, you can do something that's really exciting and really cool. You can, literally speaking, make it unhackable. So kind of love that. So we talked a little bit about gateway endpoints. Now, there's another kind of endpoint called an interface endpoint. Now, the interface endpoint is when you use to connect to other AWS services, such as the systems manager, Kinesis, your load balancer APIs. Now, again, this is some pretty cool stuff because this enables you to connect to external services that are hosted by AWS partners or customers. So kind of love this. So think about it this way. If you've got to connect to a large number of people, the interface endpoints may be your best option. And we're going to talk a lot about VPC peering. I love VPC peering. When we talk about VPC peering, what we're really talking about is connecting organizations, and there's some limitations as to why. So these interface endpoints and the private link service may actually be one of the coolest things, which we'll talk about. So interface endpoints are going to connect to these services. So they're going to be local to your VPC. And effectively what's going to happen is the interface endpoint is going to create an elastic network interface on both sides of your connections because it's got to be on the same subnet to communicate. And when you create these interface endpoints and these elastic network interfaces on the same subnet are created, you're in good shape. Now, when you create the endpoint, AWS makes it even easier for you. They do so much of the work for you, which is why the cloud feels so easy compared to the network and the data center. So what they actually do is they give the endpoint a DNS-specific name to make it even easier to connect to it. So let's look at it. When you're using the interface endpoint, you're creating something called private link, which is sort of like a private wire between these kind of information. So with regards to the virtual, so it's kind of like a virtual private line over the AWS network, and it's going to restrict traffic between the VPC and the AWS customer or partner organization. So let's look at what this actually would look like. Let's say, for example, you've got a VPC that's serving somebody else. You've got basically your customer over here on the left, and you've created maybe a shared services VPC or something like this. You take some a network load balancer in front of your servers. With Private Link, what you've actually done here is you created the ability for the two entities to talk to each other. Now, that's what we're talking about. Now, one of the things that's really, really cool with Private Link, and this was really smart on AWS to think about, is because everybody, for the most part, is using the same RFC 1918 address spaces, the 10.0.0/8, the 172.16/12, the 192.168.0.0/16. Private Link automatically uses NAT. Private Link automatically uses NAT. So that's one of the things to keep in mind. So Private Link is different than VPC peering, and we're going to talk a lot more about VPC peering, but VPC peering and Private Link in certain cases do the same, but they're not the same. And let's say I've got two entities. I've got a VPC in New York, our company, and a VPC in San Francisco. If I do VPC peering between New York and San Francisco, all information is exchanged between New York and San Francisco. And guess what? If it's my company in New York and my company in San Francisco, when we peer, I want us to exchange everything. But what if I am an auto manufacturer and I need spark plugs from somebody, and I need tires from somebody, and I need brakes from somebody else, and I need metal from somebody else, and paint from somebody else, and I don't know, hoses from somebody else, and belts from somebody else, and let's just call them wheels from somebody else. I don't know. So the wheel manufacturer doesn't need to talk to the brake manufacturer, who doesn't need to talk to the spark plug manufacturer. So, and quite frankly, they may not need to know anything from me whatsoever at all. I may just need to know the status of them. So with Private Link, I can connect to all these external entities in a very, very, very secure sort of environment. Private Link is only one service. VPC peering is everything. So how do you know what to do and what to do it? I promise you we'll talk about it. Private Link is for a specific service. Private Link is when you've got 1,000,001 connections. Don't have the ability to do too many VPC peering connections. I mean, VPC peering gives you 125 connections. You know, there's going to be customers that you're going to have 1,000 plus VPCs for, and it's going to be nothing. So you're going to have to do some creativity things in order to get these things to work based upon what you're working on. If you're new a cloud architect or solution architect, you're probably not going to run into these limitations. But if you're someone like me that's been around or working on the network, you're going to run into this 125 VPC peering sessions. Isn't that many? Especially if you have to fully mesh your VPC peers. So Private Link is going to scale more. So much more. So that's kind of one of those things that you can use, and that's why. So Private Link scales better than VPC peering. Private Link is for a single service. VPC peering shares everything. Private Link is. VPC peering does not work with overlapping IP addresses. Company A buyers company B. Chances are they're using overlapping addresses, so Private Link works. VPC peering does not work with overlapping addresses, so you'd have to change the addresses. So Private Link scales for. The limitation of your performance with Private Link is pretty much the match throughput of your servers and your load balancer. Private Link is unidirectional. You set it up in one direction and the other if you want it in both ways. VPC peering is communication that's bilateral. So that's I kind of watch you. So when we're dealing with hub and spoke environments, and we're dealing with Private Link, it brings us to the concept of a shared services BGP. And realistically speaking, it looks like some people have some questions, which I promise I'll answer, so we can make sure we get you the kind of answers that are going to go cloud higher when the time comes. So a shared services VPC. Let's say, for example, that you have an organization that needs to provide information to a tremendous number of people. you could create this concept of a shared services VPC, which is kind of like a service provider VPC. I'll show you what it's going to look like. Oops, didn't mean to. Sorry, this is not one group. So anyway, what you can see here is we've got a VPC at the top. This VPC at the top has a service that we want other users to use. So what we can do is we can set up a private link service, and our shared service, we create a straight VPC. We've got our some very fast network load balancers, for example, and we're using them to front end a bunch of servers, and that becomes a service for everyone else. So this is a shared services VPC. This is the way you would set it up using the private link service. This is how you get your communications. Now, we're going to cover VPC peering, and then I'm going to answer some of those VPC peering questions, because it looked like a lot of VPC peering questions came out. It looked like there were some people really needed some help on some of those answers, so I want to make sure we answer them really good to make sure that you walk away from this and truly learn for the day. So let's talk about some VPC peering. VPC peering is how you connect multiple VPCs. Again, I do not view the VPC as a virtual private network. I view it as a virtual private data center, because in the VPC, you put your servers, you put your storage, you put all kinds of good stuff. So VPC peering is a method to connect your VPCs over the network. VPC peering is non-transitive, and I'm going to show you what that means, non-transitive. Communication uses the private IP address space, and anytime you're dealing with inter-region traffic, it's going to be encrypted. So, secure way to deal with your traffic. So how does it work? What I was meant by non-transitive. Let's say my head is, so let's say my left hand is router A, my head is router B, and my right hand is router C. In a transitive environment, A tells B who tells C, and C tells B who tells A about each other's routes. If C knows A's routes, they can talk to each other. Life is good. If A tells B A's routes, and C tells B C's routes, but B doesn't tell A C's routes, and B doesn't tell C A's routes, nobody can talk to each other. So what transitive routing means, everybody has knowledge to everyone's information. Non-transitive routing, you don't pass the routing information. If you don't have a route to something, what did we talk about before with the gateway interface? You can't reach it. So here's non-transitive routing. Left hand tells me about a route. I don't tell the right hand. Right hand and left hand can't talk to each other. Transitive routing. Left hand tells me about a route. I tell my right hand about a route. Right hand tells me about a route. I tell my left hand. Everybody's routing information, and we're all talking to each other. All talking to each other. So now you know what is transitive versus non-transitive. So when we start talking about transitive routing and non-transitive routing, guess what? We start talking about BGP route reflectors from about 30 years ago, because it creates a problem, a massive problem. And I'm going to tell you why AWS chose to go non-transitive, which was probably the right decision for 99% of the customers. And that 1% that need to go transitive, they gave you a very good solution that we took from the BGP world. So let's look at VPC peering a little more carefully. At the easiest and most essential state, what you've got going on is simply as follows. You've got a VPC over here. You've got a VPC over here. You connect your VPCs, and then they can talk to each other. That is it. Simple, elegant, completely functional. Now, here's where it gets ugly. VPC peering is not transitive. Let's go back to here. This is a nightmare done for a right reason. For good reasons, AWS made this decision, but it can be a nightmare for you if you don't know how to deal with it. Let's go back to non-transitive. A tells B and B doesn't tell C, which means C can't reach A. Now, if A told B and B told C and C told B and B told A, everything's perfect. But we're not doing that. So if we want this to work and we want everybody to be able to talk to everybody, we have two options. If everybody needs to talk to everybody, Just like in internal BGP, we're going to need to fully mesh our VPC peers. This is ugly, because when you have to do full mesh or everybody talks to everybody, there's a formula for this. This formula is ugly. It's called n times n minus 1 divided by 2. So if you've got 3 VPCs that need to peer, it's elegant. 3 times 3 minus 1 is 2. So 3 times 2 is 6, divided by 2 is 3. 3 connections, 3 VPC pairs. Simple, right? 10 connections. 10 times 10 minus 1 divided by 2. 10 routers or VPCs, 45 connections. 100 of them. 100 times 99 minus 1. You get the point. It doesn't scale. So, but this is what fully meshed is going to look like. B tells its routes to C tells its routes to A tells A routes to B. Everybody has a connection to everybody, and everybody can talk to everybody. This is how it would work. If everybody needs to talk to everybody, you're going to have to fully mesh them, or you're going to have to use one of 2 options, which we'll talk about in a minute. Now let's go back. Sometimes your VPCs don't need to talk to each other. Sometimes you don't want them to talk to each other. So let's look in this environment. Let's say we're now the car manufacturer. We're VPC A. We connect to the tire people, VPC B, and the steering wheel people, VPC C, and the brake pedal people, VPC D, and the tire people, VPC E, and the leather people, VPC F, and the seatbelt people, VPC G. Do any of those people need to talk to each other? No. Do me, as a car manufacturer, do I need to know where I'm getting my steering wheels, brake pedals, and leather? I sure do. So I can do this hub and spoke. Now, what if all these people needed to talk to each other? What if? How could we fix this? Well, in BGP, we've got a solution for this. And we've got a 30-year-old solution for this in BGP. And guess what? When we're dealing with VPC peering, BGP peering, you now know why I wanted to do a little BGP for you guys, because it's BGP everywhere. And when I say learn the network and learn the data center, and you'll always know what to do, because everything that we see on the cloud is an old network and data center technology, I'm talking about it right now. And this is why learning the network makes you better for everything. So AWS has 2 solutions to this non-transitive routing problem. One is called Transit Gateway, and another is called Cloud Hub. Now, functionally, they're nearly identical. Basically, what both of these services do, they act like a BGP route reflector, and they enable me to take in a route and then send the route to someone else. So it basically says we've chosen to allow transitive routing. In BGP, we have something called a route reflector. So AWS has a service called Cloud Hub. I think this is a very elegant service. It is a route reflector. It's not new technology. And because it's not new technology, and because it's proven technology that we've used for decades, it actually works. So what do we love by this? So here's what you can see what we do in this environment is we've got, and if you're using VPNs, you're using Cloud Hub. VPNs, you're using Cloud Hub. If you're using direct connections, you could use Transit Gateway. You can use Transit Gateway with just VPNs, but Cloud Hub is just for VPNs. So just keep that in mind. So here we've turned on Cloud Hub. We've got a New York, a London, and a San Francisco location. New York sends routes. And you know what happens after New York sends routes to the cloud? Guess who gets to see them? Everybody gets to see them. London gets to see them. San Francisco gets to see them. Everybody's routes. So everybody's reachable. This is non-transitive routing. San Francisco can reach London. London can reach New York. The data center can reach everybody. This is non-transitive routing. Had it been Transit Gateway, it would have been the same thing. It just wouldn't be VPNs. So we're going to get to some network access lists, and we're going to get to some security groups. But it looked like I saw lots of questions popping in there with the VPCs and VPC peering and addressing. And it looked like some of the questions needed a little bit of help. So Chris, if you can walk through the questions. Jazz, can you create an endpoint from your on-premise server to S3 or other service? So basically you create an endpoint from your VPC to S3, and then you can share that information, Jazz, going back to your data center over your direct connection or your VPN. Can we connect two internet gateways to a single VPC? I don't know why you would. The internet gateway is a logical device, which means that it's not physically there, which means it's high availability and it wouldn't go away. So no, you would not connect two internet gateways. Now, there might be a time if you run into performance limitations. And again, this is where you're going to work with AWS. Everything has a limitation. Everything. Even things that have no limitations have limitations. So this is where if you're in an environment with like an AWS environment, if you have an extreme customer that might need, terabits of internet connectivity, you might want to talk to them. They may need some kind of a creative solution where they use a couple of network load balancers to load balance between internet gateways. I've not had to do that with a customer. So, but, typically speaking, I do a lot more hybrid and multi-cloud stuff. So I'm always using multiple internet gateways. But, realistically speaking, I've not had the need to because they're high availability. Now, if you ran into a performance limitation, and again, I would consult AWS on that, then I'd walk to them to see if you needed to use like a network load balancer or a gateway load balancer to go to multiple internet gateways, but I've never needed to do so. I've had to deal with hundreds and hundreds and hundreds of VPCs, but this is not something that I've had to do. Chris, you want to bring in the next one? VPC pairing can span region and inter-region traffic is encrypted. Absolutely tailor-made media.
All right, now some of these you came in before you got it into your content. So this one I think you answered. I know it came in before you got to this, but so you may want to spend just a second on it.
Sure, and that's a great question. Plus, Balwinder always has super smart questions.
Yeah, but
so
you answered it right after she posted it, so without realizing.
So interesting. So Balwinder, here's the thing: private link is for a very specific service. So you want to host one thing. VPC peering is for everything. Plus, with VPC peering, you have to have non-overlapping IP address space. And AWS was really smart with the private link service, and they figured you'd probably run into problems. So they gave you the private link, which does NAT automatically, so you don't have a problem with overlapping IP addresses. Chris, you can bring the next one. Can transit gateway work with overlapping CIDR ranges? Do you mean overlapping IPs? Well, transit gateway, nothing is going to ever work with overlapping IP addresses. So the question is, are your CIDR ranges overlapping, but not your IP addresses? Meaning it's quite possible that you've got a 10/8 on one side and a 10/8 on another side. But inside of your 10/8, you're using a 10.1 and a 10.2 and a 10.3 and a 10.4.0 on the left side, and you're using 10.0.1 and .0 and 10.0.2.0 and 10.0.3.0, then you don't have overlapping address space. You just have overlapping CIDR ranges, in which case you won't be able to send a single route, Mr. Joshi. You're going to have to send more specific routes. You could make it work, but that would be really bad IP addressing. Really bad IP addressing will ultimately mess up your routing long term. Can you make it work? The answer is yes. Have I seen it work? The answer is yes. Should you make it work? The answer is absolutely not. So do good IP addressing scheme ahead of time. If you don't, nothing will work properly. Shavini's Fun World. Something in a public subnet is reachable from the private subnet because you have a router. A router is how you route between subnets. So realistically speaking, when you leave your computer and you go to the internet, it uses a router. When you've got your servers in a private subnet, remember there's a router and a routing table that sits inside of your VPC, and your VPC has a default route that points your unknown traffic to the NAT gateway. So it's going to happen because you have a route to it. The route is the key. Asim, how does private link overcome the issues of overlapping IP addresses? Private link uses NAT, Asim. NAT, or network address translation, translates one address into another address. Private link they put an elastic network interface on both sides. They're on the same subnet, and NAT is done between the addresses. So they use NAT, and that's exactly what NAT was used for, Asim, to translate one set of addresses to another set of addresses. Chris, you want to bring in the next one? Well, Lion Lord, we don't have an option to use anything other than Transit Gateway with Direct Connect. We can't use Cloud Hub because it's only for VPN. So Lion Lord, we have two options with the Direct Connect if we're trying to use VPC peering. We can fully mesh them, or we could use Transit Gateway. But the only reason you're using the Transit Gateway is for VPC peering. Now, and you're only doing it if you're running direct connections to your various VPCs. The direct connect, typically speaking, is just to connect your data center to the cloud. So I'm not sure if I completely answered your question. If I did, great. If not, let me know otherwise. Leonard Lash, what is the difference between an EMI and an interface endpoint? Gateway endpoint connects you to S3. Interface endpoint connects you to certain AWS services. When you create an interface endpoint, it creates a network interface inside of your subnet so that you can connect to the interface. So the interface endpoint creates an elastic network interface. What is an elastic network interface? And it's really just a network card. You will need an elastic network interface to connect to a network, because if you don't have access to the network, you won't be able to use it. So hope I answered your question there. When do you require an elastic network interface? Anytime you want to connect to the network. So Shavini's Fun World, imagine you have a computer in your house and you wanted to get to the internet, but you don't have wireless and you don't have a network card that you can plug in. You couldn't get to the internet. What do you do on your computer? You enable your wireless, which is a network interface, or you enable your Ethernet card, which is a network interface. So you can't do anything without a network interface. You'll never be able to reach anything. Every server that you have comes with an elastic network interface. Every private link service has an elastic network interface. You can't access anything without an elastic network interface. So that's how you attach to the network. It's like the Ethernet card that's sitting inside of your systems. Chris, you want to bring in the next one? Will private link work across regions? I believe so. Ronald Nozo, the reason AWS is able to provide so many IPs is they're one of the world's largest internet service providers. So they've got a pretty good block of them. So they were able to get a whole lot. And realistically speaking, we'll be using Ipv4 addresses for a long time. We were ending Ipv4 when I started working in networking in 1996, and we're not ending Ipv4 anytime soon. I assume we'll be using them for the next 20 years or so. Louise, I know you said the IG is a router. What can be referred to? It can't be referred to as a switch, Louise. A switch is a layer 2 device. A router is a layer 3 device. Technically, a switch can have a router module in there and be considered a layer 3 switch. But when you're dealing with the internet gateway, it must be a router. A switch doesn't have routing abilities, a true switch. So it is always a router. Yolanda, is Cloud Hub also used to run VPN connections to your various VPCs? That is why Cloud Hub is used. Cloud Hub is used so you can run VPN connections to your VPCs in a VPC peering environment and actually have transitive routing. That's exactly what it's used for, Yolanda. Chris? Damn, thanks. I didn't know that. I have asked a lot of people and no one knew this question. Thanks. Well, you're welcome. I'm so happy we're able to help you.
That was in response to the router and switch confusion. You know, so many people, because when they're get confused on that topic.
So yeah, that's a really good point. I'm going to have to do maybe a networking workshop one day where we talk about routers and switches and VLANs, and we really spend some time on it. Maybe we configure some routers and switches and VLANs. I don't know. Maybe I'll even do a free CCNA class. We'll think about it.
Yeah. So that was the last question. I'm going to let you do your thing.
Okay, very cool. So if you're having a good time, if you can please put a like down, it really, really, really helps us from the algorithm perspective. Everything's an algorithm in today's world. And anytime anybody is able to basically help us and say something nice, it really helps us from an algorithm perspective. So if you guys don't mind hitting a like button or sharing with others, we can appreciate that. Now let's talk about some access control lists. And also, if you're having a good time, if you can put hashtag cloud hired, very good chance we'll do a CCNA. But my team's working on a couple of really, really cool free classes out there that I'm pretty impressed and proud of them for. So I know I got some people on my team. I've got somebody, I like to call him Mr. Bond because he reminds me of James Bond. He's working on something really, really great for the cloud engineering community. So we're going to have some other cool, fun stuff to be coming very, very soon. So let's go back and talk about now. Oh, and I'm reminded from Chris that at 5 p.m. we're going to have Imran come. Imran, the dual CCIE, the Aviatrix multi-cloud professional network engineer, finishing a third CCIE while he's at it, just because 2 isn't enough. He's been around and doing everything, and he's going to come in, and we're going to set up some VPC pairing and all kinds of cool VPCs and endpoints, and we're going to walk you through it and get really hands dirty, really hands-on. So it's going to be a great time. So part of our commitment to making you guys the best in the world is giving you everything we can. So we're going to do so. So let's talk about network ACLs. I love access control lists. Been using them forever. They break everything and they lock things down. And if you're smart, you don't break anything, but you got to be careful with your access control list. Network access control list. They're really just an access control list in the cloud. So on routers for years, we've been using access control lists on the routers. What do we put access control lists on the routers for? We do it to keep unwanted traffic out of subnets. Access control lists enable us to allow traffic or disallow traffic based upon a configured policy. So, like a firewall, what do you think the default policy is? Deny all traffic. Deny all traffic. So, when you create a network ACL, you're going to set up a rule, and the rule is going to be a whole lot like a firewall rule. You'll specify the source and destination address, the protocol, and the port number. Do all of you remember when we walked through the header and we talked about the source and destination address, the protocol, TCP, UDP, ICMP, and the port number, like port 4443 for HTTPS or port 80 for web? That's where all this stuff is coming from. It's in the header of the packet. The access control list, the firewalls, they're all looking at the header and the packet. So this is really fun stuff. So that's what we do. Now, I want to talk about the concept of stateful and stateless before we talk about the access control list. I got to tell you, 90% of the people that I interview get this wrong. I ask this to lots of people on interviews. If someone doesn't know stateful, I can't hire them because they're not going to know how to do a lot of things. So let's talk about stateful versus stateless. They are different. Blivik, thank you so much. So stateful means as follows. I watch. So I've got a cat, Cindy. She goes outside. Here's what she looks like. And then she sees a bug, and she jumps up and she catches it. She's on. She's staring. She's paying attention. She's stateful. What is a firewall? A firewall is as follows. She's like my cat, Cindy, that's paying attention to everything. I'm behind a firewall. Let's say this phone is my firewall. I want to go to the internet. I go from behind the firewall through the firewall. I go to www.gocloudcareers.com. I pierce through my iPhone firewall. My traffic goes to the internet. It hits the gocloudcareers.com website. And then the GoCloud Careers website stops and it comes to the firewall and it says, I'm sending Mike Gibbs back his request to the website. The firewall says, I know Mike Gibbs. I watched his traffic traverse the firewall. So it's going back to Mike Gibbs because Mike Gibbs asked for it. He's allowed. I breached my firewall and it comes back. How does the firewall know? It watched what I did. It's like my cat, Cindy. She's out there. She's staring around for stuff that's moving. And when she finds it, she gets it. That's what a firewall does. A firewall blocks all incoming traffic. It lets my traffic go through the firewall. And then when the traffic comes back to the firewall, it says, that's Mike's traffic. He went to this site, let it come back. Now the hacker tries to get into my network and he's like, hits the firewall and he can't get in. And the firewall is saying, you didn't initiate the traffic. You're not from inside. You're not allowed in. So when we're dealing with firewalls, we're dealing with stateful. Because the firewall knows it's stateful, we don't need to create a rule back that says allow Mike's traffic back because the firewall watched my traffic go out and it knows to allow it to come back. So stateful, that's what that meant. So network access control lists are stateless. And because network access control lists are stateless, meaning they're not tracking anything, you're going to have to design them bilaterally, inbound and outbound. So just so you know. Now, network access control lists are processed in order, and order matters. So I'm going to show you a good way to do it, and I'm going to show you a terrible way to do it. I'm going to start with the terrible way so that you understand the right way. Now, normally I would never show you the wrong way, but I'm going to show you the wrong way right now. So let's show you the ridiculous way. Let's create a set of rules, inbound and outbound. Rule 1, block everything, throw it all away. Rule 2, allow web traffic. Anybody see a problem with this? Rule 1, trash. Rule 2, allow. What happened? Packet came in, hit the network ACL. It said deny all traffic. It's all blocked. It's thrown away in the trash. No more traffic goes. No more traffic goes because it's blocked. So don't do that. Permit what you want and allow the implicit deny to take over. So let's do this the right way. Let's recreate this. Now, we're just going to allow TCP port 80. And that's it. Let the auto deny do it. Let's just allow what we need. Now, after 25 years experience, I'm going to give you some special secret tips here to keep you. The implicit deny is there. We don't have to write it. It's just there. All firewalls have an implicit deny. So all we really need to do for the most part is just do our permit statements and everything else is blocked. So let's go think about this. So let's do this. That's all we have to do. Now, I'm going to give you some real guidance. Don't go rule 110. Don't go rule 111. Don't go rule 112, 113, 114. Give yourself some space. I'm saying, I mean it. Really give yourself some space. Because no matter what you think you have, you're going to create new rules. So let's say we want to allow TCP port 80 in for a web server. And then let's say 6 months later, we've got one user in China that's trying to hack us. And we just want to do an access control list to block one user. We can. But if we have no space, we can't. So maybe 110, 120, 130, 140. Note what I wrote here is only rule allow in and rule allow out. So let me show you this real quickly here to put it into context. When it comes to security, it's not a network access control. It's not an ACL. It's not WAF. It's not Shield. It's all of it. And then some. All of it. So it's not an either or. It's all of it. But let's look at what we're talking about. We're going to have our internet gateway, which connects us to the internet, our virtual router, and a network ACL protecting the subnet. So that's it. Network ACL protects the subnet. Now, behind the network ACL, we're going to have like a host-based firewall that protects the server. And that's going to be a security group. But everybody say it with me, even if you're home. Network access list protects the subnet. Security group protects the host. Everybody with me. Network access list protects the subnet. Security group protects the host. I don't want anybody to forget this. Test question. Network access list protects the subnet. Security group protects the server or service. So keep that in your mind. So now you know what is a network access control list. So let's talk about security groups. Security group is just like a network access control list, but instead of being applied to the subnet, it's applied to the server. Now, the good news, the cool stuff about these security groups is they're kind of a stateful firewall. So that means you've got it. Here's your server. You've got your security group on the way into the server. All you have to do is allow in your rules, because when your traffic comes into the server, the firewall is stateful. So it's going to say, okay, allow in and allow out. So your security groups are stateful. So you only need to allow them in one direction. Stateful doesn't mean you only need to allow in one direction. Stateful means track the state of the connection. But the net effect of tracking the state of the connection is you only have to allow it in a single connection, which makes it really, really great. So that's how we're using these things. So let's walk a little bit. When it comes to high security environments, you're going to use it all of it, all of it, all of it. So security groups support allow rules only. Because remember, you got an implicit deny. It's a firewall. Allow this in. Block everything else. All non-allowed traffic, guess what? Denied. All rules are evaluated here. So when you're dealing, for example, with the security group, it's going to look at all rules. When you're looking with an ACL, as soon as you hit that deny, it was just trashed. So, keep these things, just keep that in the back of your mind. Let's look at it architecturally speaking one time. I'm going to go back to a picture. It's going to look a lot like the last picture, but not exactly. And here's the reason. Here, we've got our same internet gateway. We've got our network ACLs protecting the subnet. We've got our security groups now highlighted in blue protecting the server. Now, let's talk about the dirty little secret of security. The second you start putting in your firewalls, your IDS IPS systems, your access control lists, your security groups, your host-based firewalls, your malware protection, you start disabling unnecessary services, you're going to do a lot. When you start getting into these environments, what ultimately happens, you will break things. It's just a matter of when. Now, how do you debug these things? You're using packet sniffers or protocol analyzers, but AWS gives you some very useful tools. One of my favorite AWS tools to use are something called VPC flow logs. Now, there's all kinds of great CloudWatch things. Look, AWS gives you some great monitoring things, but I'm a network person. What do network people like me look at? We are used to looking at Cisco NetFlow. Cisco NetFlow tells us a lot about the traffic that's going through our systems. So we network architects were looking at NetFlow. AWS created their own version of NetFlow. They called it a VPC flow logs. This is awesome. You can find the data that's coming into your network through your network. It's kind of great. So your flow log data can be put into CloudWatch. You can stick it in S3. This is incredibly useful when you're diagnosing connection problems. It can help you find overly restrictive security group rules. It can help you monitor traffic that's reaching your systems. It can determine what's blocking, what's allowing. So this is just really cool stuff. Totally love VPC flow logs. They feel just like NetFlow. So basically what happens, you set up your flow log, and it basically, you tell it the type of traffic to capture, whether it's accepted traffic or rejected traffic or all the traffic. Then you tell it where you want to push your flow log data, and then you can see it. So I'm actually going to share with you a picture that I took from AWS. You can see the source because it is their photo. You can see where we got it. I recommend you go read that article. It's a good one. And that's why I left the article name there. And that's why I used an AWS graphic with the name, because I wanted everybody to be able to go there. It's a great thing. So if you look on this flow log graphic, you can see very clearly, you find the account, the source, destination address, the protocols and port numbers, and we can see, okay, rejected being blocked, say, for example, by something being allowed. So we can find out, if we've got an overly restrictive access control list. So these are one of the things that I like. So, next, what we have tomorrow, which is going to be some really meat, we're going to get into some meat about VPNs and direct connections, and we're going to talk about all the architectural pieces and the routing pieces, and we're going to have some real depth, and we're going to have lots of fun. We will at some point probably do some security if you guys want, and maybe we'll do a whiteboard session where we map you through how do you really lock down an enterprise. We may do one with regards to how do we do it with cloud native tools, which will work for a good number of customers. And then maybe we talk about how would you secure like a high security environment, again, using some of the tools that we're going to get from the marketplace. So there'll be lots of things that we can do. So a couple of thoughts. For those of you that have joined late, don't worry. You're going to be able to watch this on YouTube. You can start the beginning of the video. Tomorrow, we can again come where you can catch up tonight and then go tomorrow. I'm going to answer some questions in a second, but I want to remind everyone at 5 p.m., Imran Takur is coming. Between Imran and I, we will have 3 CCIEs, and we're going to do some VPC peering. We'll set up some VPC endpoints. We're just going to have some fun. We're going to demo how to do all this really cool stuff. So that'll happen at least once, maybe 2 or 3 times this week. We're going to give you some surprise cloud infrastructure engineering work in addition to just the cloud architecture work, because I want you to have it all. So Chris, if you want to bring in some questions, let's finish the day off with some questions.
All right.
If you guys have any questions that we didn't answer or more questions, I'd rather spend 20 minutes answering your questions or whatever it takes. I want to try and do what I can do, even if it's to help out. Question: how much network traffic flows from servers in an OS scaling group to an application load balancer? How much network traffic? Watch the base. That's totally dependent upon your servers. You can have servers with 100 gig network cards that are running at 100% 100 gigs each server, and you could have hundreds of those servers in a high power environment. Or realistically speaking, you could have less than a mega traffic. So it's totally based upon the application traffic that you have, and that's going to be based upon your application. There's realistically nothing that I could give you to guide you. That's the questions where you have to ask the customer. What is your traffic pattern? How many users do you have? Where are your users? How many million hits do you get per day, per second, per week, per month? Only what's the average web page size, or what is on your web page? Is it static? Is it photos? Is it videos? It could be anything.
So the next question is not specifically related to this, but I thought it was a very important one.
Vikram Nanda, how many years experience to become a cloud architect? It's a pretty interesting question, Vikram. And I'm going to give you the honest answer. It's not how many years experience you have. Experience doesn't matter. What matters is competency. So let's say you have two people. Let's say you've got a 14-year-old that broke into the Pentagon, or a 50-year-old with 25 years experience in security that can't do penetration testing, wouldn't know what a firewall is, and doesn't know what an IDS is, but they've been working there and they've got 5 certifications. Vikram, you're going to hire the 14-year-old that broke into the Pentagon. So Vikram, I've got to tell you, in the last 6 months, I think I've gotten about 100 people hired as cloud architects, and I'd say 30 or 40 of them have never worked in tech in their entire life. And it didn't matter. So it's not how many years of experience are required to be a cloud architect. It's, are you capable and competent? So here's what's going to have to happen. First and foremost, you're going to need a couple of things. You have to be competent. What does competent mean? It means extreme knowledge of the network and the data center, knowledge of routing, knowledge of switching. And I'll give you the full answer. You need to have about 3,000 to 5,000 pages of routing knowledge, specifically from the books Internet Routing Architectures, Routing from Bassam Halabi, Routing TCP/IP Volumes 1 and 2 from Jeff Doyle, as well as the Stevens book on TCP/IP. I would say you need about 500 pages of NAT on top of that. I would also say you need to learn QoS. You need to learn VPN technologies, IPsec technologies, all kinds of direct connections, all kinds of ether channel, port channel, link aggregation groups, to say the net. Then you need to have deep knowledge of firewalls, IDS, IPS systems, VPN concentrators, load balancers, all of this stuff. You got to have that. And I'm going to tell you, we're talking about 75,000 pages of reading to have the competency. When I take people, we're dealing with about 500 hours of training. Then what we have to do is as follows. That's 50%. Now, most of the cloud architect job is not so technical. Everybody has it in their head that it's technical. And all my people that get hired, I have to basically tell them, not such a technical job. So the next thing that needs to be there is you must have extremely good executive presence, exceptional communication skills, high levels of executive presence, the ability to write, the ability to sell. So when you get these interviews, here's what you need to do. Next, what you need to do is you need to have experience that matters. So for example, I have my students VPN into a data center, and I have them build everything. My students build a cloud from scratch. Every cloud architect should know how to build AWS from scratch. And if you don't apply for a job. You don't have the competency. You should know how to build a firewall. You should know how to build a VPN concentrator. You should build an Active Directory server. You should know how to federate that Active Directory server with that whole cloud that you built yourself. You should work with server virtualization, work with containers, and all that should be on your resume. Then, Vikram, the key is to skip HR. Now, I got to tell you, a lot of my students get hired by AWS. One was with me for 3 weeks that just got hired and never worked in tech in his entire life, but he took a technical account manager role. Another one recently was with me for 3 weeks, and he was a network person who instantly went there, but he had good networking background. So regardless of the cloud providers, and I've got students that are working in all of them, it's the competency. Now, I got to tell you, when somebody brings you in for an interview, they assume you can do the job. And all these people, Azure brings people in with no experience for an interview. Google brings people in with no experience for an interview. And AWS brings new people in for an interview. And if the new person does a great job on that interview, they get hired. Now, if the new person goes on that interview and is terrible, doesn't have the competency, do you know what they say? I'm sorry, you don't have no experience. Experience is a proxy for we don't think you're competent. That's when people say, come back when you have more experience. Now, HR is another story. You have to, and then we'll talk about how do you skip HR. You have to understand HR's problem. HR are good people. They're highly educated people. A low performance company like a cable company will get 3,000 applications for a single job. A good company like a Google or an AWS or a Cisco, they might get 5,000 to 10,000 applications for a single one. So because of that, they put all these roadblocks. And by the time they interview someone, they're not necessarily the right person. It goes to the hiring manager. The hiring manager interviews these people and they're like, I can't hire these people. They're a jack of all trades and master of none. So what most organizations do is they hire an executive recruiter. Vikram Nanda, on Friday, I will have some executive recruiters on my channel. We use executive recruiters. We have now 300 executive recruiters we use for the students in our Cloud Architect Career Development Program. The executive recruiter will have you meet directly with the hiring manager, skip HR, and then it's up to the hiring manager. And when the hiring manager asks you a series of questions, it's up to you to answer those questions properly. Your executive presence, your communication skills, your emotional intelligence, your competency will work. And then we got to talk about the competency. I'm going to tell you this, what's covered in the AWS Certified Solution Architect Professional is about 8 to 10% of what you need. That other 90 to 92% needs to be taught. And if you don't have that, again, so it's not the years of experience, because someone could have been a software developer for 20 years, and that's not related. But someone could have been a network engineer for 2 years, and it's highly related. So anybody can do it. I've got nurses that have done it recently. I've got people from sales that have done it recently. Anybody can do it. It's not your experience. It's how hard you're willing to work. You got to be willing to do that work. It's about 500 hours for me to train someone with no experience to get them hired as a cloud architect. And 500 hours is a lot. Can you use a network ACL for a private subnet instead of having to use the egress? I'm not really sure what you mean now. You can use network ACLs on all subnets. So you're going to use an access control S on all subnets anywhere all the time, anytime you want to protect a subnet. So I'm not necessarily sure what you mean. It's not just to connect to external networks. Do I use the AWS Network Access Analyzer? Not at all. I use tools that I've been familiar with forever and a day. We use protocol analyzers. I use routing tables and routers and switches, and I ask questions. But to be fair, I'm not a cloud engineer. I'm an architect. So, I'm not exactly getting hands-on as an architect. I do it as an engineer. But no, there's very good, strong industrial tools that I use for most of these things. And they are things that network architects and engineers use. They're not coming from the cloud provider. SM7, do you set what traffic to allow in and out of the host with a security group? Yes. If so, what's the point of having specific traffic? Okay, so defense in depth. So 1 is none, 2 is 1, and 3 is greater than 2. So here's the way you lock down systems, SM7. First thing you do, let's say you've got a content delivery network. Let's say we're using CloudFront to lock our systems down. We'll use Shield for DDoS protection. Now behind that SM7, we're going to put a firewall around us. Let's pretend we're in the castle. Let's say we put a 300-foot wall up to keep people out. That's the firewall. Why do we do that? Because we don't want to get anybody in. Now SM7, let's say we've got somebody that rolls over the firewall. Behind the firewall in the castle, they have a moat. And it's filled with alligators and sharks and dangerous animals. Why? If anybody breaches the firewall, they fall into the moat and they get eaten by sharks and alligators. And let's say you've got someone, they're like a Navy SEAL. They get over the firewall. They swim through the moat. They don't get eaten by the alligators or the sharks. So you put a couple of lions back there, and the lions, are there to eat them. The lions, the moat, the sharks, consider them to be your intrusion detection, intrusion prevention system. Now behind that, because this guy that got in or girl, it's bad, they want to harm you, then you use a network access control list. But guess what? This guy beats the network access control list. So guess what? Now you use a security group. and the security group's going to block them. But this person's smart to get past your security group. So inside of your server, guess what else you've done? You've put a second host-based firewall in that server. You've disabled all the unnecessary services and TCP ports. You put some anti-malware protection, and it's still not enough. Somebody's knocking at the front door of your server, so that's where your IAM comes in. SM7, are you allowed in? No, you're blocked. So why are we doing this? We're doing layers, 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 layers. You know, we're going to use a lot more layers than that SM7 to lock down the system. It's going to take us layer after layer. Why do you use multiple layers? Why do you use multiple layers to dress for the cold, to trap the heat in? Why do you use multiple layers for security? Because people will keep breaching everything that you do, and you want to make sure they can't break in. That's why you're using multiple layers, SM7. And there's a lot more layers that I haven't even talked about that we would add. So it's not just a security group or a network ACL. It might be 15 times more than that we need just to create an appropriately secure environment. But great question. How does the network ACL protect the subnet? Well, it's basically like a firewall rule that says this traffic is not allowed in. So if you've got a subnet and you basically only allow traffic to one server and you only allow, say, port 443, realistically speaking, what's the word I'm looking for? You would just block it or keep it out of there. So I hope I answered your question. SM7, thanks, Mike. You've said this time and time, but you didn't get it. No, as long as you got it, that's okay. I just wanted you to get it. However that takes, it doesn't matter. I'm just thrilled you got it. Okay, Chris, let's see what else we have here. Is there any others? Because it looked like I saw somebody asking some more questions.
The next couple of ones are not so much content as career. So
okay,
I saved them. And not really sure exactly on this one, but I'm going to put them up back to back because they're from the same person.
Sure.
Because I asked for clarification, and the second one is what I got. So.
Okay, so let me answer both of those things. So you want to go back to the first one? Certification. So people look at me and my perspective of certification. I want to make it really clear. I actually like certifications. Now, I want to be really clear what I mean by liking certification. Certifications can show that you've gone through the effort to learn the name of a vendor service and how to configure them. And when you lack experience, adding some certifications to your resume is amazing. Amazing. Because it can help get you an interview. But I want to be really clear. What is tested on a certification? The name of the service and how to configure that service. That is what is on certifications. And if you are a junior cloud engineer, and what you do is you configure S3 buckets, that certification is really helpful. But here's the problem. As architects, we don't configure anything. We design. So knowing the name of the service and how to configure it is completely worthless for us, the architects. Now, still the certification is good because it helps us get the interview, but it won't get us hired because it's not relevant to what we actually do. What we actually do as architects is design, and there's really no design in there. Now, the other problem with the certification is they don't explain what it is. So the certifications are phenomenal. If you've been a network engineer for the last 10 years, and you know what is a firewall, and you know BGP, and you know OSPF, and intermediate systems to intermediate systems, and software-defined networking, and RSVP signaling, and VLANs, and 802.1q tagging, and NAT, you don't need any of this. Then you pick up one of these books. Like, I love this. It's a nice book for the Azure expert. We're always reading everybody's content to see what we like, what we don't like. In fact, I got to tell you, the only content I've ever seen that was any good was produced by the Cybex books or the Cisco Press books. The rest of the content out there is a little on the fluffy side, but I do like these kind of books, Cisco Press books. The Cybex book I found to be pretty good as well. So you still need to get certified. Now, here's where certification hurts people. If the certification is in your field, it makes you look great. So Mr. Chattery, we've got a certified solution architect professional and a Cisco certified internet expert. Now we've got the brand of a cloud network architect. looks good. Expert network thing, good cloud thing, we look solid. So those certifications are worth it. Now, you want to be an architect and you study SysOps, which is maintenance, DevOps, which is automation, application development, Alexa. You've got now 10 of these certifications and they're all in 10 other careers. Now these certifications make you look confused and unfocused and unattractive to the employer. So getting the wrong certifications will hurt your salary and hurt your job and hurt your employability. So it's not that certifications are worth it or not worth it. It's getting the certifications that build your brand. So, want to do cloud security? Here's what you do. CISSP in the Certified Solution Architect Professional. Note, I didn't say the AWS Advanced Security. Not that I don't love the AWS Advanced Security, but it's not big enough. I need you to get the big stuff. I need you to know how everybody does it. And that way, when you work on AWS and Azure and Google, because as a cloud architect, you're going to work on all of them, you're going to know the underlying. So it's not that I don't love AWS certs. I do. I love Google certs. I love Azure certs. I love all of them. But I want you to know what a network load balancer is for real. Separate the elastic load balancer from the cloud load balancer and really learn what is a network load balancer and what is an application load balancer. And that way, when you're in your hybrid cloud and you have an F5 load balancer, you'll know what to do. When you're in AWS, which is incredibly good cloud, you'll know what to do. And when you connect to the Azure cloud as well, you'll still know what to do. Because let's face it, a single service provider is a single point of failure, and you're going to use multiple service providers. So it's not that the certification isn't great. It's that I need you to be competent first. So get just enough certifications. Now, here's the last part of this. Here's what I need you to understand. Certification on average can raise your salary approximately $10,000 a year. Soft skills training for an architect can raise their salary about $50,000 a year on average. And emotional intelligence training can raise someone's salary on average $30,000 per year when you look at statistics. So if you do the extra certifications, and you can have a $10,000 impact over your career, over 30 years, that's $300,000. But by focusing on those higher skills, those more enterprisey architect skills that are worth more, you can add an additional 2.4 million to your career. So it's not that I don't love certifications, it's that I want to build you the best career. And as a career coach who's focused on getting people hired and promoted and paid more, I place my efforts on the things that maximize the return on the time that's spent by my client. So certifications, yes, you should definitely have the AWS Certified Solution Architect Professional. If you're going to work on AWS, that's kind of my version of the minimum certification. But then get something else in the industry you want to become great at it. So I hope I answered your first question. Now, Chris, was there a second question?
It was just a clarifier.
Okay.
You got it.
Okay.
Got it.
Can I explain the ephemeral ports? Not elegantly in the short period of time. What he's actually referring to is, you may hit a web server at port 80 and it may start answering at a certain number of ports. But when you're dealing with an access control list, you don't necessarily have to worry about the destination port as much as the source port, and you know what the source port is. You don't necessarily have to worry too many things about ephemeral ports, unless you're dealing with a poorly designed application that's going to use 1,000,001 ports and you don't know what they are. In which case, then you're going to have to open up a lot more ports on your access control lists, realistically speaking. So kind of work with that. So I guess I'm kind of thinking, mind opening talk, wonderful, greatly appreciated, wonderful. I want to give you guys everything that you need. Jeannie, it's always incredibly good to see you. Thank you so much. Okay, so I want to let everybody know that at 5 p.m., I know we're flooding you with free content this week, but we like to give free and we like to watch you people get hired. We like to hear you guys doing great in your lives and your careers in every way. It makes us super excited. So at 5 p.m., Imran's going to come back and we're going to have some fun. We're going to geek it out. We're going to do some configuration. We're going to have some lots and lots and lots of fun. So it's going to be fun. One day we may even bring in some Cisco routers this week and do some BGP configuration. I'll see what we can do. So hit that like button. Tell others to subscribe, and I hope to see you all back at 5 p.m. tonight. Everybody, I can't wait to see you all. See you tomorrow, see you tonight, depending upon which time zones you are. We're just happy to see you so much. If you're having a good time, can you type AWS Advanced Networking course in the window? And I'll see you all tomorrow. Thank you all so much. Thanks, Jaws. David, I'm so thankful you joined us. Kapta, I'm so happy you were here. Pal, Winner, I'm always happy to see you.
I'm going to come on screen because they keep saying Mike and Chris. So I'm like, I'm going to come get my recognition.
So Chris, so everybody that's here, Chris, let's thank you. Chris is my chief operating officer. Chris works really hard to make sure my students are successful. I wouldn't even know where to be if Chris didn't even tell me where to be there. He had to send me a text message. Hey, Mike, did you actually stop your class on time so you can eat before you can be here? So we got to thank Chris.
No. I didn't send a message. I sent a message to the entire class to make sure that you stopped so that they could get you to stop.
That's true. Asim, obviously that'll help you class the AWS Advanced Networking exam. It's a relatively easy exam, but I strongly recommend a practice test, but it's a pretty simple exam.
Yeah. So we'll be back at 5 o'clock. So an hour and 43 minutes from now.
Aqua, great seeing you. I see you Magas here. I've seen some of the names. The ones that I've seen, I've said hello to, but there's been a lot. So wow, it's so good to see you guys here.
Yeah, lots of comments. I'm trying to make sure I get them all on here before we close out. I like to make sure, even if it's just a split second, that everybody gets up.
I like, honestly.
There we go. Chris is the man. I like that.
I like that one too. I think you did great.
All right. They just keep
Amaranth, I'm happy to see you. Whitfield Davis, that's a name I'm happy to see.
Yeah, share the glory. There we go.
Alonzo, it's good seeing you there.
There we go.
Seeing your name, Alonzo. I haven't spoken to you since yesterday, so it's been a long time.
We got to come up with a costume for me now. Chris the superhero.
I think we can do that. Although I'm thinking Cindy needs a LinkedIn page. We're going to have to do that someday soon.
Yes, I agree. Yeah. All right. Well, Central Time, Pacific Time. So 5 o'clock Eastern Time. So 4 o'clock Central, 3 o'clock Mountain, 2 o'clock Pacific, and whatever time Arizona decides it wants to use.
Yeah, I never know what time it is over there because I've got a couple of time zones in Mountain Time. Yeah, some places actually are on Pacific Time, some are on Mountain, but it's only during daylight savings time.
I don't even know when daylight savings time is on or off or what it is. I just know, something.
I just go where I'm told.
Yep. All right. I finally got caught up. Bye, everybody.
See you. Any of those. See you all tomorrow or tonight if you want the bonus round. Take care, everyone. It's been such an honor.